Hello, ma'am. Should we wait for a couple of minutes for a few more attendees to join?
Yeah, sure, sir. We can wait for 5 minutes more, and we can start by 9:35.
Okay, ma'am. Ma'am, a quick question. So, the files which I emailed yesterday, were you able to receive them and upload them?
Yeah, absolutely. Today's course materials were given in a drive link, right?
Okay. Yeah, yeah,
So
ma'am.
yeah, so we have downloaded that files and
Perfect.
uploaded it in our own drive.
Awesome, awesome, ma'am. Thank you. And ma'am, I was a little bit confused whether the quizzes are on Thursday or because the new schedule said on Monday. So there was like,
Yeah, it is on 5th of April. 5th of
okay. So
April.
it's on Monday now.
Yeah, yeah.
Okay, so yeah, because earlier we had a communication about Thursday, so that's why I was. So I've already sent you the first one. That remains the
Yeah,
same.
yeah.
I'll send you the same.
Okay, sir. Okay, sir. Thank you. Dear participants, there is one announcement. Okay, the attendance sheet which we circulated yesterday has some changes to be made. So it will be made during the next 2 hours. So we request you to please have patience and check the updated list by today afternoon. Thank you all. We will start the session by 9:35. Thank you.
Okay. It's 9:35. So I guess I'll start by addressing some general concerns. As already conveyed to you by Firoza ma'am, The attendance and all that has already been looked into by the EICT Academy. So please convey your doubts there, and I'm sure they'll figure it out and they'll sort out all your queries in there. So the concern regarding the Docker and OpenLane installation and everything to that respect. The OpenLane and the backend part of the course has been purposefully kept in the second half of, in the second week of this program. So it gives you a decent amount of time to figure it out. So even if you have not been able to install it till now, don't worry. There, as I've seen, some of you are getting errors of the permission denied and stuff like that. There are next 3 days are off, and the next session is on Monday. What I'm going to do is sometime tomorrow, I'm going to send around a link, a few resource material to be for everyone to be able to play around with it more, try to get the installations correct. So we are going to help you in the next 3 days trying to get that installation up and running. That is point number one with respect to the Docker and the OpenLane part of the course. With respect to the part of the course which has been done till now and which will be done today, so yesterday we worked everything on USIS. So only thing that was needed was an Linux environment on your end, which we have conveyed in the beginning of the course. You will not be able to do anything without that. So if you had Linux environment, you could run USIS. And after that, the files which were needed, so the examples were already on the drive. Following that, we will be exploring RISC-V code today in serve environment, which has also been uploaded in the drive. So in today's drive link, you will see there is a serve zip. Please download that. We will be exploring in the later half of today's first lecture. The serve design. It's one of this core which I am asking us to explore this today because this is the one which you guys will be playing around with it during the second week of this course. So the way the course is structured is we will be, from the instructor side, we will be handling a RISC core. We will do all the implementations on it. And in the second week, when we do the OpenLane, so from the instructor side, we will be handling a RISC core and we'll do everything. But from the participant side, you will be handling another one and you'll be trying to sort out issues in that. And then we'll be actively trying to debug and your design issues there, and you'll be trying to fix them real time and learn how the actual implementation flow is run. So that's the general flow of the course. So in order to facilitate that, you need a design which was uploaded in the drive yesterday, and please go and download it. It is in today's lecture link. Using that, today we will be just exploring it in USIS. As I pointed out, we do not need the Docker and the OpenLane. If you guys are facing issues, we have purposefully kept it in the second week, so we will have next 3 days to sort out some of your doubts. Following the same train of thought, next today what we'll do is there's a question about the online test. The online test is on 5th April, Monday, after the second lecture. After at around 1:30, I think, towards the end of the lecture, there will be a quiz. That's the first one. And today, what we'll start doing is we will dive into the concepts of timing constraints. Yesterday, we got an overview of what synthesis means and how can you visualize different stages of it using the USIS environment. I would advise you to have your Linux environment open in the background because we'll do a little bit of switching back and forth between the slides and the Linux environment as we did yesterday as well. So Today, in the first half of this today's session, we will start exploring what do we mean by the timing constraints and with respect to synthesis. So yesterday we have already looked at what synthesis mean, how different optimizations are done in synthesis, and we explored different stages of the flow using the uses tool. Today we'll look into timing constraints, and then we'll start the exploration of RISC-V core, which has been uploaded in the drive using USIS environment today. So that is the general plan for the first half, and then the second half, Puneet will again continue the hands-on discussion on the IO files and some other topics. With respect to, there were some concerns with respect to the IO files and libraries. The libraries are already in the drive. So Sky 130 basic PDK was already in the drive. You can get it obviously through the OpenLane installation and making the PDK. But we already took the part which was important for yesterday and today's discussions, and that is already uploaded by E&ICT Academy in the drive. So in yesterday's link, there should be a PDK. Please go and download that with reference to yesterday's IO files, and also with respect to when you do the library mapping and the DFF lib mapping. So that's the with respect to the logistics and what we are going to be doing in the today's and the forthcoming sessions. Now, following along, the today's session, what the plan is, as I mentioned, is the timing constraints and synthesis part. In the timing constraints and synthesis part, what we want to do is, as already explained yesterday also by me, we would like to overview input delay, output delay, environmental attributes, how these attributes scale to different things as you are on different levels of hierarchy in an SOC. So at the top level of SOC, at the block level of SOC, at the multiple block level of SOC, how these environmental attributes will be varying, and how do you capture them correctly in the picture for the input and output delay aspects. We will be covering that. And then we'll be using the similar concepts in the following lectures for doing STA on the RISC-V course. So that is the plan to move forward. Okay. So timing constraints. So the general synthesis flow usually is you load the design and technology data. So that would be the design and technology data would mean the Verilog files, that would be the design files, and then there are technology files which were explained by Puneet yesterday. For example, the library files, the TF files, all, and the standard cell left files. So all of that is technology data, and I think he'll continue the discussion today on the rest of them. And obviously the design data is your actual source code of your RTL. So you have to load all that. Then before you synthesize the design, you're supposed to apply the timing constraint. So now this is a little bit tricky with respect to the open source environment, because your open source environment is able to pull off synthesis without timing constraints as well. So today we will actually be exploring the RISC core without the timing constraints parts. It is able to do a synthesis without the knowledge of what path is timing critical. So, but when we go into the OpenLane environment where the timing constraints with have been integrated using OpenSTA, then we are able to pull off STA on that design together with it. So we will circle back and close this loop using that with the open lane environment. Now, I have a question to the participants. Let's see if people are awake and following along. If we do the synthesis without the timing constraints, what is going to go wrong? So means why do we care about providing timing constraints? So when we actually go to the backend flow, will we observe any issues if we do synthesis without timing constraints? Anyone wants to answer from the participants at attendee list? Let's see if anyone is awake. Okay. So metastable states, I'm okay, that's a fair point, but that can always exist. Mallikarjun, I'm not sure with the transient. Okay, but okay, there are correct answers with respect to timing closure not achieved. That is the main point. So there are multiple paths in timing paths in your design, and if you do not synthesize with the timing constraints applied, it is very hard for you, your backend tool, to then further optimize them, because backend tool does not do any logic optimization. All the logic optimization is done by the synthesis tool itself. If your synthesis tool did not do any logic optimization, then it is very hard for your backend tool to be able to fix timing using just buffering change. We'll go into what different stages of backend is, but if you're you need to understand from yesterday's discussion as well, the logic optimization occurs in synthesis. So this is the part where the logic optimization happens and nowhere else. So if timing constraints are not correctly applied at this stage, then going forward, you cannot change your logic hierarchy, logic part of the design, how it is structured between different pipeline stages, for example. So all of that cannot be modified anymore. There are other things which are happening in the backend flow which are not pertaining to logic optimization at all. Because you cannot do that, so the freedom to change design to meet timing reduces by great extent. So as researchers and designers who are trying to use this open source environment, how do we approach this problem? So then everyone would be like, so if we really cannot meet timing very well using this open source environment, why should we even use it? The answer is, again, we need to go back and to the same point which I was trying to explain yesterday. If if uh, if your even your synthesis tool in open source environment does not have great optimization capabilities. It can do simple arithmetic optimizations and mux-tree optimizations and stuff like that. But the onus of writing better RTL to be able to get uh, better better post synthesis results is up to you. Now, if that's isn't that the whole point from researcher and creating new fancy designs even in industry, that you want to write better RTL? So if the how you pipeline, how you meet timing, how you define your data paths correctly, that all that falls on the shoulders of the RTL designer. You cannot expect your your synthesis tool will play a very minor role. It will do only minor optimizations, and the only thing it will do then is map your RTL into a gate level netlist. So the answer is, if you're not able to properly apply timing constraints before you synthesize a design, you need to be able to fix the issues correctly from the RTL side itself. You need to write better RTL. You need to, for example, if you're specifying adders, you need to specify clearly how the adder is constructed to be able to meet timing. So we need to understand what synthesis does. Synthesis does it breaks down your RTL into an intermediate stage. It does optimization there and then maps it into a gate level net. Now, that optimization part is what is seriously restricted in open source tools, but it also gives you as a researcher and industry professional an opportunity to be able to optimize your RTL, to be able to write it in a way that meets the specs better. I hope you are able to appreciate what I'm trying to say, and most of the answers here are correct. Naveen is pointing out that we will not be able to perform clock resynthesis, means that is a backend thing. We may be able to do it, maybe not. Sure, the second point Naveen is making is correct. And okay, let's move along. So before we do the synthesis, usually we are supposed to apply timing constraints. We'll go back, circle back, and close this loop using the open source environment, open lane environment in the next week. Okay. Now, let's try to any question. Let's see if anyone has any questions at this point, and then we'll move along. Honestly, Malikarjun, mostly startups try to work with open source tools. They are still catching up, and there are products out of university environments which come out of open source tools. This is just because they're free, and big companies have money to buy tools. Not everyone in the startup has money. Wasim, we are not going into the in-depth RTL level implementation within the course of this in the duration of this course. We'll try to go from the RTL level implementation and forward. We'll visualize it using YOSIS today, but we'll not deep dive into RTL. Writing better RTL, we'll have for your processor size, we'll try to schedule some other lectures in the future for doing that. Any questions with respect to what we are doing, why we are doing, and I can proceed with the constraints part. Sure. That is one of the, so Naveen is asking if open lane based results are acceptable in the research domain for publication. For sure. The results are actually on the conservative end, so it is always acceptable. Latrice is asking if open source tools are other than open source are able to meet timing constraints if not properly applied. Sure. Again, the problem remains the same, right, Latrice? If you do not apply the timing constraints, then you have a suboptimal design post synthesis. Depends on if you've written better RTL, then you're able to meet timing. If there is only limited with on the implementation backend side that you can do. So apart from that, even the next question is how do we succeed in the physical design without optimization? So your logic paths are not optimized. There is only some minimal amount you can do during your backend flow, and again that's what I'm trying to point out. You have to write better RTL to be able to pull that off. So as researchers who are writing better RTLs, this is a way for you to be able to even visualize that. Okay. Okay, so Vishnuvardhan has an interesting question. So how do we know that we have done correct synthesis? So this is a very interesting question which goes into the verification side of things. It is not a target for this course, but I would still like to explain because participants should understand the general overall flow. Okay, so basically, you have different stages of your design, from behavioral to RTL to your gate level, which comes out of synthesis, to post PNR. There, in order, so right now we are going into the implementation flow side of it. In parallel to the implementation flow, there is a verification flow which also runs. And after every design stage, in the implementation flow, we only do the static timing analysis. But in the verification flow, we have functional checks, we have all kinds of other checks which make sure that the design is still up to the spec. And there are also conformance checks, which are, some of them are in open source, some of them are not, which are done in parallel to your implementation flow. So as I'm pointing out, just even tackling a design side of things, we are only following one branch. If you remember Puneet's session, he showed you that we are only tackling one side right now. We'll try to come back on the other sides again, but you need to understand there is a complete parallel design cycle of verification on this. There is complete RTL design optimization on it. There is a complete implementation flow side on it. We are tackling the implementation flow, and you need to be there is a constant back and forth between different teams, and on isolation, if you only one person cannot be able to pull off all this, obviously. Okay. There are a lot of open source tools for verification. Shilpi will we can send you some references later. Which level of system implementation do we have? Highest level of optimization. Wasim, please. I'll come back to your question later. Please explain it more. I don't get it right now. Let me now go into the block setup and timing constraint part of things. So now block setup. Let's see. Now, if we want to specify setup timing constraints, what do we do? Okay, so what is the environment we are dealing with? We've been given some design specs, and first we'll try to assume that we have a single clock or a single cycle environment. Okay, so that is the first thing we are going to assume, that we have a single clock or a single cycle environment, that we have a one clock in our design. So if you remember on yesterday's slide, I showed you there are multiple clocks, there are divided down versions. Let's ignore that for the moment right now. We'll assume single clock. What is our objective? Our objective is to define setup timing constraints in all input and output parts of the sequential design. Okay, so let's try to understand what that means for now. So those paths will be some register to register paths. They'll be starting from input ports, going to all input logic paths, and starting from output logic paths, ending in output ports. So it's all words right now. In the next few slides, I'll try to explain what all of this means. So basically, what you want to derive out of this slide is we are trying to constrain the design on setup. We are doing it under the bounds of a single clock for now. We want to visualize what all different timing paths exist under such a design spec, and how do we make sure that all of those paths are constrained. Okay, so that is our objective. Okay, so you need, also we want to point out some things. Any design tool, whether it is an open source tool or even a commercial tool, assumes a synchronously clocked environment. Usually, all of the implementation flows break or do not support asynchronous designs, apart from marking that certain blocks are asynchronous to each other and letting the RTL designer handle them. So by default or by their nature, the tools run static timing analysis, which runs under the assumptions of synchronous design. And they do not support asynchronous design. The only things you can do is mark blocks as being asynchronous to each other, and then you have to make sure from RTL perspective that they follow that trend. Now, having said that, so what does that mean? That it means that input data arrives from a positively edge clock design, and output data goes on a positive edge. So someone is sending us data on their positive edge of the clock. We are also getting the same clock, and we are sending the data out on our positive edge of the clock to someone else. Let's see what this means. Now, that was all words. Let's try to visualize this, okay? So I will take questions after this slide, basically. Okay. Let's try to first visualize what we are trying to talk about. So what do we have? So currently, this is your world. So this is all you care about, and this is your world. So assume this is your SOC, okay? What do we think? What all do we want to constrain in terms of timing paths? If this is your complete SOC, what do we want to do here? Let's see. So if this was your SOC, what do you want to do? So let's see what we have here. We have input port X, input port Y, and a clock port clock in, and output ports E, F, and clock out. Okay. Then there are certain register sampling stages, and there is combinational logic in between them. Okay. So we have path one, which is starting from our input port, and it is going to the deep in of your flip-flop. And this data must be coming from someone. As I mentioned in the last slide, this is a data pin. This must be coming from someone, and we are assuming that they are sending it on the rising edge of the clock. And when it comes here in our design, we are again assuming that we are sampling it on the rising edge of our clock. So someone sent us this data. This data followed some path, and after that, there was this path one at our end, and we are sampling it on the rising edge. So if you're following along this discussion, then you must be realizing now there must have been a lot of path here before X, right? After someone has sent us this data, before it reached X, there must have been a lot of things here. So let's try to see arrow options. Yeah. Okay. So there must have been a lot of things here before this came in, right? So suppose someone sent us here on the rising edge. We are sampling on the rising edge, but there must have been a lot of things which happened here. How do we, if we live in just this environment, this is all we have, right? How do we tell the tool what was here, right? We need a way to tell the tool what was here. If the tool doesn't know what is here, it will give you wrong answers, or your design will not meet timing. On similar lines, question is, if we are not clocking it at all, so this is this part of the design, right? Yeah. So this part of the design at the bottom. Let's see. Yeah, now it's good. So let's delete all that. And let's go to, I'm not sure why it's not working at one go. Yeah, okay. So this part of the design at the bottom, how do we constrain this? In order to be able to constrain this, it is coming from somewhere, it is going to somewhere, that it doesn't have any clock. What do you do now? How do you constrain this? You need to tell the tool what is here, and you also need to tell the tool what is here. We need a mechanism, a language, a method to tell the tool what is here, right? So we need to figure out what to do there. If we follow the same train of thought now, we have this point where we are transmitting on the rising edge here. We are then passing it through this logic, and we are capturing here on this point and the rising edge again. Now, if we have this, then the question is, how do we tell the tool how much time does it have to do this part? We need a way to tell how much time does the tool have to do this. That's the question. How do we do that? So after specifying all of these, whatever I have discussed, can someone point out which path have I not covered? If you're following along, can someone tell me what did I miss? Sure, we have not. Yeah, okay. So people are and thought process is in the right direction. We did not cover this path right yet. How do we constrain this path? So in order for us to constrain this path, as I discussed earlier, we are transmitting on the rising edge. After we transmit on the rising edge, the data goes through this. But after we are sending the data to someone, right? And if you're sending the data to someone, what is here? How much can exist here before it is again captured before a rising edge of the clock? We need a mechanism for us to be able to tell the tool that information. So that is why the whole notion of constraints exists. Constraints is a method for us to tell the tool all this. If we do not tell tool all these pieces of information, then it doesn't know all this. So there is no way for it to be able to figure out how does it optimize logic in synthesis stage, and also the rest of the implementation in the backend flow to be able to meet timing, because it doesn't have a notion of time. We create the notion of time using constraints. Please understand that. If you live only because when you are doing any synthesis or implementation flow, this is where you live. So if you are here, you need to visualize how do you tell the tool what does the external and internal world look like with respect to timing. Anyone has any questions up till now, or would like to add or question any point here, or doesn't understand what we're talking about? Static timing analysis, Shreyas, is the only way which is scalable. I mean, there are and can be other ways to do timing analysis, but because as the design complexity increases, static timing analysis till now has been the only way which is fast enough, scalable enough that you can run it on big designs. There is obviously dynamic timing analysis, and there are other kind. You can always do functional simulation and rerun the synthesis flow, right? There is no one stopping you. You can add timing you can do transistor level simulation and augment it with your synthesis, but that would be so slow. So people have picked this level of abstraction. This is how we'll specify the timing using the timing constraints, and that's what that's the definition which has come out. Rajesh, as we already discussed, that was missing, that deliberately missing, and that's what everyone was pointing that out. Okay, so Naveen has an interesting question. It's saying, is it necessary that E must be fed to somewhere else if I define it as output then? So the tool doesn't know where it is going, right? If you have created a port, so if you have an output port, the tool doesn't have any way of knowing where it is going. So if you live, again, I want you to understand, you live here. The only piece the tool knows is this. Tool is in this location. If the tool is in this location, it's only able to visualize this. You need to tell the tool what exists here and what exists here. If you cannot tell the tool what exists here, it will not be able to map timing on them. Now it is up to you. If it is not connected anywhere, don't tell the timing. If it is connected to something, specify it somehow. And the next question is, this STA, does it depend on system clock, which we are using? Yes, for sure. Oh, system clock. What do you mean by system clock? Please explain, because system clock has a lot of meanings. So please explain a little bit more. Would be nice for me, then I'll answer this. Okay, why is my pointer messing up? I have no idea. Okay, let's see. So yeah, means if your computer is fast, you'll run the STA fast for sure. Then what is the difference between static timing analysis and dynamic timing analysis? So if you have a notion of if you have a notion of different edges and how they, it means if you create a notion of time, then it's dynamic timing analysis. Right now, there is no, you are referencing it to a clock and you assume all possible transitions with respect to it. You are not doing any simulation. There is no notion of something changing, basically. It's a very complex concept going into dynamic timing. Let's not tackle it right now. You can look it up. Okay. Register to register path, there any other IO? Sure, there can be multiple input outputs between them. This was the, so Lakshmi, this was the most simple form of description I have come up with. Obviously, that this path too can be really complex and is usually really complex. Okay. Now, again, to reiterate what I was talking about, design compiler breaks the design into timing paths that have starting point and ending points. Starting points are input ports other than the clock port, and ending points are output port other than the clock port. So X and Y are starting points, E and F are ending points. And also clock pin of a register. So this was a starting point, as you already saw. This was a starting point for the path which was not shown here. Any point in the sequential design not on the clock port. So which one would that be? So in this would be that point. So let's point that out. So this would, wrong color. So this would be that point, ending point, which is covered by this. I hope everyone is able to follow this. So someone's asking y is equal to f. Trajan is asking y is equal to f. So y is not necessarily equal to f, right? There might be some logic here. There might be another gate which is low. So Z, which is coming in here. Let's try to use, not sure why it is. Yeah, okay. So at this point, there might be other signals coming in. So I'm just trying to show that there are combinational paths which may or may not be clocked. How do you time them? That is the important part of the discussion which we have to do. Okay. What is the second? Clock pin of a register to any input. Clock pin for register. So this is the clock pin of a register, right? This is the input. This is where the path is starting. Similarly here, this is where the path will start. So okay, I see no more questions here. Then we'll move along. Okay, so these are all the paths which we captured in the last slide. Just to reiterate them again. Now, let's start with how do you constrain the register to register path. Now, anyone wants to take a guess? How will we be constraining a register to register path? Let's see if anyone is awake and trying to follow along. And let's take a guess. How will we constrain the register to register path? Let's go back. Path 2. This is the path we are talking about. What do you need to tell the tool to be able to constrain this path? Everything. So as I mentioned, you are living in, let's try to visualize where we are. The tool knows everything about this part of the design. If the tool knows everything with respect to, so it knows this, it knows this, it knows this, it needs to know how to optimize this. What do you tell the tool so it knows how to design this basically? Excellent. Okay, all correct answers. So the tool needs to know what are the delay here. So it can pick that up from where? It can pick that up from lib files. The setup timing information for this, that also tool can pick up from the lib. What the tool does not know is if I fire on the rising edge here, and if I capture on the rising edge here, what is the time I have from the rising edge to rising edge, right? If I transmit on something and capture on the rising edge again, how much time do I have between two rising edges? So what is that called? That is called a clock. So it needs to figure out what is the meaning of a clock. Till you do not tell the tool what is the meaning of a clock, it has no way to figure out how does it optimize this part of the design. Okay, so that is what we are trying to now capture. Let's go forward again. Okay, constraining reg to reg path. So this is the path which we are trying to optimize. And as we saw, if the logic part of the information and the technology part of the information is already provided. So I'm assuming that you have already loaded the design data, which tells us what kind of logic we have. And if the library file exists, then it knows what is the delay for them, what is the setup time for them, and everything. Then the only piece of information that you need to tell the tool is what is the clock with which you are transmitting and capturing, and then you are able to constrain all the path tools. And you need please visualize this well, that if you have an SOC, most of the timing paths are actually of the kind of path 2. So most of your design paths are usually register to register paths. I hope you are able to appreciate that statement. So if you're able to clearly convey what is your clock, you would have probably constrained more than 90% of your design paths already, or actually more than even 95% of your design paths, because usually in a design, in an SOC, most of the paths are of path 2 kind. They are register to register paths. They're internal to the design. They're sampled. They're transmitted by a clock internal to the design, sampled by a clock internal to the design. So if you tell the tool what is the clock, you have done 95% of the job of constraining already. I hope everyone gets that. If you don't, please ask me. Okay. And here, any tool will try to. Okay, that is already covered. Okay. Okay. So now that we are here, now that uh, we uh, now that we know that in order to be able to constrain the timing paths correctly, we want to do what? We want to most of the timing paths are register to register paths. In order to constrain them, if we specify the clock correctly, we can constrain most of the timing paths in our SOC. So following that argument thought process, we want to understand what is a clock, and we want to understand how does it behave, like how do we tell the tool nicely what it is, what are different features of it, so that we are able to do a good job of defining a clock. So also I want to point out that some of the lecture material which we are discussing here is useful in the clock resynthesis part. So as I mentioned in the previous earlier sessions, that we will have some degree of freedom of moving things along. So don't worry about it if not everything is captured today, because we are already capturing some of the lecture material which was needed for, say, clock resynthesis part, defining clocks and stuff like that. So we'll cover everything. It's depending on the audience and depending on how the course is flowing, we structure things to best cater to the explanations. Okay. Now let's start by defining what is a clock. Okay. So how do we define a clock? That's the question we are trying to answer. What are we trying to do? We are trying to constrain this path. Please have this in mind before you constrain anything. Okay. It is very important to understand why we are defining clock. We are trying to constrain this path. We are trying to figure out what is the maximum delay we can have in this path. Okay, so this is this is a spec which comes from the system side. Okay, from the system, someone says you need the design to run at 500 megahertz. So in order for us to be able to meet the application which we are targeting, the design has to run at 500 megahertz. If the design has to run at 500 megahertz, then we derive the effective clock period, which is 2 nanoseconds. Okay, so 2 nanoseconds is what you have. In an ideal world, if you had transferred from this point on a rising edge and reached this point on a rising edge, you would have had 2 nanoseconds to deal with everything in between. Obviously, when I say deal with, there is the setup time, there is this clock to queue delay. To deal with all of that, you would have had 2 nanoseconds, and also the delay here in this blue block. Now, when I say ideal world, you would have had 2 nanoseconds. I want to see I want the audience to take a guess. Why would we not have 2 nanoseconds? If someone told us you won't have to run this at 500 megahertz, why do you think we will not have 2 nanoseconds to meet this Tmax path? What will stop us? What is it that we are not accounting for yet? Sure, that's a correct point, Malikarjun, because rise time and fall time are not ideal. So that will reduce the time we have. Completely agreed. What else? Anyone else wants to take a guess? Is there something else? Agreed. Setup hold. So that is the setup should be captured. Ankit has a very valid point that we need to probably have a slack when we capture to create some margin. Agreed. Interconnects and wire delays are a valid point, which need to also, because till now I have not shown them, they would exist here. Vishnuvardhan has an excellent point. Jitter. All clocks are not idle. So we'll try to visualize where that jitter comes from. Perfect. So Naveen also is pointing out rise and fall time. Okay, everyone is in the correct direction. Perfect. So everyone is understanding that we do not have complete 2 nanoseconds to solve our problem. This Tmax, it cannot be 2 nanoseconds. Let's see what it can be. Okay, let's try to visualize this. Now, if the only piece was the setup time, right? So if let's try to draw here again. If we fire on from this location and it goes this way, like pointed out, if the only constraint we had was this 2 nanoseconds and that it has to set up before this setup time, we pick this 0.4 nanoseconds from the library. And if we pick that, then for how much do we have? We have 1.6 nanoseconds left with us, right? If we were only worried about meeting the setup. So, and also Puneet will take a deep dive into this setup in a multi-logic kind of environment means, but I'm just trying to give you an overview to make you understand the importance of clocks. Okay. So if we have that, then the Tmax would have been the T clock 2.2 minus 0.4, and that is 1.6 nanoseconds. Okay. I think everyone would be able to follow along with this. So that was the one of the things you were mentioning. Why do we not have 2 nanoseconds? Because we have setup timing constraint, which comes from this flip-flop. Then moving along, how do we tell the tool what is the definition of our clock? We need to first try to figure out what is the definition of the clock before we actually try to tell the tool what are the non-idealities involved in it. Okay, so in order for us to tell the tool what is the definition of a clock, there is a command. This is a standard across industry, open source, everywhere, specifying timing constraints, and it's called create clock is the command, and you can tell the period, and then you try to tell where are you creating that clock. So right now we are creating the clock at port CLK. This is the port. So you say get port CLK, and that is the standard method for creating a clock. Now, once you have done that, then the tool understands that there is now coming back, there was a question by Wasim, I think, was asking what is the difference between dynamic timing analysis and static timing analysis. An example of that would be once you apply this at this clock port, right, the tool does not go about putting a transient waveform here and measuring its effects. That would be something to do with the dynamic and transient analysis. The only thing that the tool does is it then knows between this transmit to this receive, it has 2 nanoseconds. That is all that this creates. Okay. So now, how will the clock apply itself in the design? Let's see. If you have this, then let's assume this is the clock, an ideal clock. We have not captured the rise time and the fall times yet, as mentioned by one of you. This is what gets applied over here. We have 2 nanoseconds to deal with this piece of information. By default, a 50% duty cycle is assumed. Clock object of CLK, which is the same name as the port name, is created by the tools unless you specify with the name option, which we're not doing over here. Now, we can always do name clock and then the object will become CL clock. Why am I describing objects here right now? Because in the last lecture, I already told you what objects are. Okay. So we have 2 nanoseconds over here as shown. This is how it will create it. Now, this was all the ideal clock behavior, just capturing the setup timing requirements on the capture side. Now, what do real clock distributions in SOC look like? We have a clock source. That clock source gets further divided, further spread like this. Usually a simple technique is called H trees. So this is a symmetric clock distribution. If it starts here, the wire delays are symmetric, and you put buffers at every junction in order to make sure that you get decent clock driving strength. I will come back with this diagram again when we talk about clock tree synthesis. Okay, now at the end of it, not ideal behavior is maintained, not symmetric distribution is maintained, because if you have millions of flip-flops, if you create a H tree toward till the end, there are system implications with respect to power, as we'll look into those with respect to the clock tree synthesis. But in general, this is one possible strategy for the clock tree distribution. Okay. Now, this is again an ideal SOC distribution. So what is going to happen? First thing is there will be a skew between block here and a block here. We need to capture that if we are constraining block 1 with respect to these 2 blocks together. Again, there will be noise. So these buffers are not ideal. So anytime there is a signal transition through them, there'll be supply noise, there'll be process noise, there'll be all kinds of noise. If there are all these noises, then these noises will actually exist in all of these buffers. If the noise exists in all of these buffers, then what will happen is as the signal traverses through this path, this signal will look something like this. Suppose if we say that the rise, there is obviously I'm capturing a rise time here. If the signal transitioned like this, then if in an ideal world, the signal was supposed to transition at this point of time, there'll be some uncertainty that it can transition before it or after it. And as we go further down the signal chain, this uncertainty keeps on growing because more and more noise keeps on getting added. So if we go back, as we travel further down from the clock tree towards the block, this uncertainty on where the transition can happen, where your rising and capturing edges do occur, is growing. So you have a growing uncertainty where these edges are. We have to capture that in our clock spec to be able to meet our timing. Okay. So this is what your real clock would look like. And we have to capture this noise uncertainty. Now, what are the points to remember? Let's see. The synthesis tool, even if whether it's commercial, whether you do an loop back using OpenST or anything, if it considers a timing constraint, it will not buffer the clock network. It assumes that it is ideal. Okay. So it assumes that it has a 0 rise and fall time, it has 0 skew, it has 0 insertion delay or latency. And for correct result, one should model it with estimated skew, latency, and transition times. If we do not do that, then the tool will not be able to have correct assumptions. And if the tool does not have the correct assumptions, then your synthesis of the design will not be up to the spec. And as we mentioned already in the previous slides, that your PNR will not be able to then further meet the timing. Okay. So I hope you are able to appreciate that 95% of the paths in the design usually are register to register paths. If you tell the tool what does the clock look like correctly, then we capture all of these issues, then you are able to constrain all of this nicely. Okay. So as I'm trying to point out, we have not done clock pre-synthesis yet, so the tool doesn't know what the rise, fall, skew, insertion, delays, and all those are. So we have to model them. Okay. So prior to layout, what needs to be modeled? We need to model the clock skews that are modeled as uncertainty in tools. We need to model the latency or insertion delays that are modeled as source and clock port latencies. We need to model the transition time there using the realistic input signal transition time. So we are going to look at each one of them one by one. Okay. Now, before I dive into all of them one by one, I would like to see questions because I see there are quite a few. Let's see. Okay, how do I? Combinational logic. Let me see. Where were we in? Okay. So Naveen will come back to the combinational logic part. Please wait for a bit. Zakir, that CLK has to be in get port CLK, the port name of in your design hierarchy for the clock. Effect of cell delay, net delay, duty cycle, etc. Tmax, how to deal with. We are coming to that. That's the whole point of this course. I mean, we'll come into all that. Money, and then again, combinational, we'll come back to that. Yosis tool with respect to reports, timing reports, we do it using the OpenSTA framework. Puneet will be showing you all that in the upcoming lectures. Then Suri Krishna is asking me to consider the metal line delay. Okay, that is captured in the implementation flow using the backend side of the things where we actually do the metal lines. So is it for more timing constraint simulation? Is it possible to model timing constraints in simulation completely and correctly without the knowledge of layout and hardware? So that's an interesting point. So basically, what the way the timing constraints are usually captured on the first go are you do a conservative job of it. Basically, you try to be conservative. So you try to keep a slack of 10-20%. You try to make your uncertainty higher for the clocks, as we'll see going further. So if you are on the conservative side, obviously, if you do not know the complete layout or hardware, you cannot do a good job of it, but you start with a conservative approximation. Setup and hold time, same as insertion delay. No, they're not. We'll come back and look at what they mean. Okay. So that was all the questions up till now. Okay, so let's see. Let's start into little bit detailed description of clocks. Okay. Modeling clock skews, uncertainty in tools. Let's start with that one first, okay? Let's start with that. How do we model clock skews, what the clock skews are? And as I told you, a lot of these slides are similar to what we need to understand from the clock tree synthesis perspective. So we'll recapture some of these concepts when we are doing the clock tree synthesis part of our work. Okay. So if our design pre-layout looks like this, our design post layout would end up looking something like this. We have buffers which are inserted between the clock from the clock port to different clock pins of different registers. Now these buffers, right? How do we model them? Because one of these buffers might have some delay, though the other one might have some other delay. There might be different wire lengths associated in them. Obviously, this is post layout, right? There are actual wires involved now. So if there are actual wires and there is a skew associated with it, we need to model it to be able to do a good job during synthesis itself. So we are defining the parameter called TS. This is our uncertainty basically, is clock skew. This is what the clock skew is. Then we have something called jitter. So if there is timing noise associated with these buffers, whatever the highest bound on that is as it progresses through the clock redistribution, that is captured in jitter. And then in order to do a conservative job, whatever margin we want to keep, we capture that in the uncertainty itself. So the uncertainty is skew plus jitter plus margin. So you capture all of that in your uncertainty requirements. And in order to specify this, the way is set clock uncertainty setup TS get clocks. And now you are please understand that you're applying it on a clock object and not a port object, because you have created an object with the same name as your port. Then you apply the value of the uncertainty on a clock object and not on a port object. People mess this up a lot of times, which creates issues in their scripts. So you apply this on a clock object. So any questions on this uncertainty, why we are applying this, what does it mean? Please do ask me. Because I see no questions right now, I'll move along. Then the point to remember is that by default, the value of uncertainty is 0. One can, so if there are multiple clock domains like I was showing you, sorry, one moment. Okay, so like I was showing you in the SOC perspective, if there are multiple clocks, you can always set uncertainty between the clocks. So say from clock 1 to clock 2, there are ways to do that. If you do not do a setup or a hold tag on things, then unless you specify it setup or hold, then default uncertainty gets applied on both setup and hold. Now, after Puneet has had the discussion for setup and hold time a little bit, I would like to come back and discuss, should we apply the same uncertainty on setup or hold both, or should we not? Please try to remember this when he's trying to discuss setup and hold with you. It's a very interesting concept to visualize. What does setup mean? What does hold mean? Should we have same uncertainties? Considering that the definition of uncertainty is what? It is jitter plus margin plus skew. Should we have the same values or should we not have the same values? Try to visualize that aspect when there's a setup and hold discussion going on. After that setup and hold discussion, we'll come back and try to answer that question. Okay. So basically, we are trying to model the clock uncertainty, and unless we specify a setup or a hold tag, it gets applied to both the values. Okay. And I want to again point out that it is applied on a clock object and not on a port object. That's a common mistake a lot of times people do. Okay, so an example of this, again, going back to the same perspective we had, we are only living in this design for now. In this design, if this is your clock, we have created a clock object with set uncertainty using setup of 0.2 on clock CLK. So if we fire on the 0, if we're capturing at 2, we have reduced the amount of time we have to capture, so that we have say that the capture happens now at 1.8 and not at 2. So the amount of Tmax we have is the arrow should have started from 0. That is my mistake. But the setup time of 0.06 then gets further subtracted from 1.8. Okay. So if it gets subtracted from 1.8 and not 2, then the effective Tmax you have is 1.74. Now the setup check, so the amount of time the tool has to do this Tmax path is 1.74 based on these constraints. Uncertainty is not assumed on the launching edge. It is assumed on the capturing edge always. So you get rid of the time on the setup capturing side. Okay, so any questions on this slide or up till now, please feel free to ask. I'll give everyone a couple of minutes to get familiarized with this slide and ask questions, because this is very important. Please feel free to ask. Okay, so questions. Trish is asking, is the clock uncertainty equal to clock skew? It is not equal to clock skew, as I pointed out here. It is skew plus jitter plus margin. Okay. So yes, Akhil, I can quickly repeat the slide. Naveen is asking how does this value come from? That's an excellent question. So where the value comes from is basically this is from a system level spec. So a lot of times you have to assume this from prior experience based on what your clock distribution strategies are, which we will look in from the CTS perspective a little bit. So you need to have a little bit of prior knowledge from the backend perspective, little bit of size, layout size knowledge, little bit of system spec requirement knowledge, what kind of clock source you have, and you try to assume this value. So it's somewhat assumed, somewhat from prior knowledge. You try to take a conservative guess on that. So someone wants me to repeat this slide, sure, and I'll do that. But apart from that, why is there no uncertainty? Okay, so excellent question from Rajan. So why are we not assuming uncertainty on the transmit edge, right? Why are we only assuming it on the capturing end? So that's the way STA is done. Basically, you need to understand that's the method. The tool assumes one side to be idle, the other side to have all the variation to be able to do the STA on it. So Puneet will again come back to it from the STA perspective, but you need to understand that's how basically STA is created to tackle with noise and uncertainty. So now that a lot of people are asking margin as well, so I'll explain that. So what we have in this uncertainty definition is the R jitter plus Q plus margin, right? Margin means whatever extra timing slack, whatever conservatism we want to create in our design, we put it in uncertainty itself. So if at the end of timing closure, if we had kept like the extra margin in an uncertainty of 1 nanosecond, and if we did not meet timing by half a nanosecond, we had kept 1 nanosecond margin. So we are like, okay, we are fine. We don't care about it because we already had a huge margin. We are again within the margin bound. So that's why we keep margin. Coming back to why we went back to 2. So if we transmit it at 0, because there was an uncertainty of 0.2, we do not know whether we will capture at 2 or 2.2 or 1.8. It can go in any direction. So from the setup perspective, we'll take the worst case and we'll say we'll capture it at 1.8. And then we'll further subtract the setup time from that. And that will lead us to 1.74. Basically, we're trying to capture the worst case from the setup perspective. There'll be more explanation on the setup and hold time from this perspective again by Puneet, detailed explanation. Don't worry about it, we'll come back. Right now, I'm trying to explain it from the perspective of how do we set the clock uncertainty and why, what is clock uncertainty? Okay. So I think all those questions were captured. Okay, then modeling the latency or insertion delays. What do we mean by latencies? There are two kinds of latencies. One is from the clock port and its source. So that is modeled using set clock latency source. And the other one is a network latency, which is within our design, that is pre-layout. So I'll come back and visualize this a little bit. And that is defined without the dot dash source tag on it. Okay. Two kinds of latencies. One, source latency. This is, let's try to visualize what this one is. Suppose you have a design and your design gets the clock from some clock source, right? That can be a PLL, that can be off chip. So whatever the latency of your clock source to the clock port where in the design you're living in, that all that latency is captured in source latency. The network latency captures the internal distribution latency. Till you have done the layout, you have to capture it using the network latency. Then in post layout, the constraint goes to set propagated clocks. That's a post layout latency. Okay. Following along in that discussion, so this is the network latency part, as I explained, and from the PLL, this is the source latency part. So here we have set clock latency source of 3 and set clock latency max of 2 as the network latency for our internal distribution. If nothing is mentioned in the command here, then it will be considered as a network latency. Okay, any questions up till now? Otherwise I'll move along to the third point, the clock definition. Okay, just to reiterate some facts, clock network delay is seen, you will see, go back to the default timing reports. It has source latency plus network latency included on it. And of this clock networking delay is both source and network, and clock network latency is just one of these. This is just terminology perspective, which people get confused over. Just wanted to reiterate that. Vishnuvardhan is asking, network latency contains clock buffers, right? Yes, it contains the clock buffer distribution latency, but since we have not done any layout yet, so we need to assume a value there on what is the worst value it can be so that we do the setup checks correctly. And Lakshmi's question, is it done by designer or synthesis people? This is done given by a designer or a system level person so that synthesis people can actually apply it correctly. So a lot of this has to come from prior experience on what can be a conservative value to assume it, since you have not done any layout yet. Okay, so moving along, the last point we want to consider from the theoretical perspective today is the modeling of the transition time. You want to apply a realistic input signal transition time. So you have a clock pin. That clock pin is going into different clock. You have a clock port which is going through a buffer distribution post layout. This is post backend into different clock pins, right? When it actually goes through buffers into a clock pin, then there is an actual rise time to the signal, and we have to model this rise time correctly. Otherwise, we will not be able to do a correct synthesis. We have not specified our constraints correctly. So set clock transition max TS, this is where we are. That's how we specify it. And this way we will be able to more accurately specify the clock to Q delay, because if you do not have the rise time correctly, we will not be able to model the delays of the cell correctly. So if now I want to circle back to the first lecture on the CPP sim, where I showed you that rise times are important for us to be able to model the delays correctly. If this rise time is not correctly specified, our delays would be completely off. And you can actually go and simulate that in the CPP sim environment to capture that same thing. Okay, so that's with respect to the modeling of basically transition time. So though we have captured the three requirements with respect to the clock. Now what the way I want to proceed is I want to actually open USIS. I want us to actually load the design using the commands which we discussed yesterday to serve core on your end. I want everyone to be able to pull that off, to be able to do that, and then visualize different design hierarchies on it and see how complex that design is. And why I said that 95% of the paths are actually internal timing paths. And if you model the clock correctly, all of them would be captured. Then later on in the next sessions, we will actually try to apply the rest of the constraints, the input side, output side, and also the clock constraint on those, and see how using timing reports they are getting constrained and you're getting the timing analysis correctly on that. So all the claims I made, we'll try to visualize them from the OpenSTA perspective. But right now, I want you to open that design and visualize the complexity and how there is the clock is able would be able to capture, because most of those will be internal transitions. Okay, so let's switch over to the Linux environment. While you guys do that, let me stop sharing. Wait, let me see if there are questions. There are questions. Uri Krishna is asking how the three latencies are estimated. The latencies are estimated. Okay, so how the latencies are estimated, not three. So the latencies are estimated based, as I said, on some of the prior experience, some of good estimates, and based on what we expect the layout to end up looking like. So please understand that design is an iterative process. You do not get it right the first time. You do a design, it fails because of something. You did not estimate the latency correctly. You did not assume the transition time correctly. You go back and fix it, and then you do it again. Then you move a little bit forward. Then you fail somewhere else. We will also see this when you guys actually will try to run serve through the backend flow. You will also face similar issues, and we'll try to do this iterative process and try to fix things. So that is why you need to appreciate that you do not know these when you begin with. You try to take assumptions, the best case guess you can, and then you do the design. And after you're done the design, it definitely fails somewhere. When it fails, we need to learn how do you circle back and try to fix the values on the right direction, and then based on what you learned, and then try to move forward. So it takes multiple iterations to get a design through a design cycle. How does these buffers provide clocks with different properties like rise times at the register input? Provide Yes, so in the lib files, all of them are captured, Rajan. But since during synthesis, we do not have actual buffers, we need to tell that value. This is, as I mentioned, all post layout. You do not have that available yet during synthesis. So clock late, Naveen is asking clock latency at the rate cases clock itself sees before and after some late come into design. Is it? No, Naveen, this is not margin. Clock latency is a separate constraint completely. So what clock latency is this basically. So if your clock starts from a PLL and there is some source latency, it goes into your block after that source latency, and then internally, whatever the worst case distribution latency would be, that is captured using the network latency. This is not same as skew. It will be more, you will be able to visualize it more once you have a multiple blocks and more SOC view. Rajan, it varies design to design. Let me stop sharing. I request everyone to open their Linux environment. Let's try to load, sorry, the design. Where did it go? Okay. Let's see what do we have here. This. Give me a moment. I would advise everyone on their end to load the Linux environment as well. And also, I want everyone to have the serve files which were uploaded on today's link. Please download them, have them available. I hope everyone is able to see my Linux environment. I will change the properties and make the text a little bit bigger so that everyone is able to see this. Okay, now here we are. Okay. So what am I referring to? Let's see, wait a second here. Let me get the Q&A out. Okay, so the files which were given to you look like something like this. So you should have a directory called serve where there is a directory called RTL, and you should have all these designs with you already. So you should have serve top with you already. Okay, so I hope everyone has this and follows along with me. If you have not been able to download or set it up, please, I request you to please do that. Things are starting to move really fast, and if you are not doing this downloading beforehand and setting up things, when I tell you, it would be very hard. Now, there is basically what we are trying to do is we'll try to load this design and go through the synthesis process for this core in using the TechLib. So the TechLib, which one am I referring to? The one which Puneet was showing you yesterday. Let's see, it is, which file is it? It is, there is also this which has been provided to you. This was provided to you yesterday in the drive. You can go ahead and download this. This is an openly available PDK, which is available, and we will be actually mapping into the lib available in this library. Okay, so what we will also do is when we do STA later on in this course, we will actually map it to different libraries. Puneet will actually ask, the reason we are doing this today's synthesis here using nicely on this design is then Puneet will actually ask you to map or run synthesis on your cores in different libraries. So say FF at 165 at 100C or TT at 100C at 1.8 volts. So all of these are different libraries possible. Puneet will ask you to map into them. And then he will request you to run OpenSTA and observe difference in timing reports. And at that point, you should be able to quickly run synthesis and then observe timing reports. So it will be really hands-on as we go forward. So please be able to run these tools. And if you are not able to complete these during the session, I advise you to go back and look at them and try to run them. Till now, the doubts have always been on the OpenLane installation. We'll try to fix them, but mind you, we have not used the OpenLane till now at all. So everything till now is quite easily installed, and it's just YOSES. And also all the files are in the drive. So go and download them, run this, because you will be using really real-time this from the next session. So there's a question about CCS noise lib. Interesting question. Puneet will answer a little bit about these libraries with noise in his session today, but in general, there is noise characterization in the libraries. Other libraries, there is no noise characterization, so that is all. So there is system noise characterization as well. Some additional information in the lib, basically, another form of it. Okay, so if we are now in the serve directory, I hope everyone has it. Really hoping everyone has it. Not, please go back, because this course is going to get really real time and hands-on from now on. If you do not install tools, if you do not have these packages beforehand, it will get really hard. And if you have not practiced previous days' work, it will also get really hard. I'm reiterating it. Okay. So we'll run YOSES. We run YOSES. So what did we have last time? Last time, what we did was we did the first step, which we did. Can someone tell me what do we do? How do we load the design in YOSES? I will ask you and I'll type those commands here. Come on. Can someone tell me what is the first command to run to load a design in YOSES? Awesome. Read Verilog. So read Verilog. I have worked with the design, so I know what is the design top. So I know the design top is I would want to add no latches for the sake of correct synthesis. Then I want to do serve top, because I know that is the top. So what we see is successfully finished Verilog front end. We are able to create RTIL representations for different blocks in the design. Okay. So we are able to do this. Now, at this point, what I want to do is I want to visualize some of these. Okay. Let's start from the top itself. Let's start visualizing from the top and see what happens. Please try to follow along and do it on your own side as well. So what did we say? We said show, stretch to send the inputs on the left, outputs on the right. The command which you can add is width. The tag which you can add is called width. What this does is it shows you the width of a bus when it is a wire. Next, I want to actually visualize serve top. Okay, I know what happened. Give me just a moment. I forgot to start my display server. Give me a moment. I'll stop sharing and do that and then rerun this. Okay, that should be better. Where are we? We're here. Okay, share. My bad. So Rajan, we are inside the RTL folder. I'll redo this. Let's see. CD project this. Let's go in serve. Let's go in RTL. We are here, Rajan. So we'll be looking into serve top. Before we do that, let's start into USYS. Now we go into USYS. We do read Verilog as everyone is pointing out. Please do it at your end as well. No latches. Serve top. Successfully done this. Now I'll do show serve top. I want to add dash stretch dash width on this. Okay, now the design loads up. Interesting. So many things going on here. What do we want to visualize out of this? The first thing we want to visualize is there is a clock port here. That clock port is going. I want to only show you the things which we talked about today. And then as we go forward in this course, we'll talk and visualize this a little bit more. Clock over here, if I point to it, you'll see that this is going into a lot of design. This is going into this first one, which is called your ALU, sorry, decode. Then it is going into your mem. This is going into the serve state. And where else is it going? It's basically getting distributed everywhere in the design. So if you had not done a good job of modeling this clock, and your timing analysis during synthesis will be all wrong. Please appreciate the complex, the fact that you have to model the clock well. And then there are bit widths pointed out in different paths. This is a serial processor which we are talking about. So let's not dive into the details of the processor, but what I want you can also do something like instead of serve top, you can go and serve ALU. And what you get is something which looks like this, which is more visualizable. Again, here you have a clock which is coming into the ALU and which is then going through the ALU operations. A lot of times students ask me, how do we actually go and visualize an RTL? So passing that RTL through the serve simple synthesis flow and then doing this graph-based representation is a very nice and easy way of doing it. So let's take a use case. Suppose you want to do what? You want to be able to change this ALU a little bit, right? Maybe you want to change the adder in this ALU to something which is more suited for your requirements. You want to optimize just the adder. You want to substitute the MAC unit in this. So how do you visualize it? You just open the design this way and you just go about, okay, what signals are going in there rather than going through that extensive Verilog. It's very easy to boot it up in yours and just visualize it. And I've actually noticed that this is faster than most of the commercial tools. Even for most of the commercial applications I do, I use Yoast to visualize all my designs because it is so fast and you're able to visualize all the timing parts and I know what to do where. So I hope everyone is able to get this. This is your ALU. Then similarly, you can do something like serve state. And this is your state machine there. So everything exists. You can individually go into these blocks, visualize them, and this gives you a really powerful platform to do it. Naveen, I'm not sure about the VHDL parser on this. I know they used to have one. It was also broken for some time. I'll need to check. Okay, now who is going to tell me what is the next command we run after read verilog? Okay, so proc is the next command I want to run. That is correct. Okay, so let's do the proc. Proc, which one? ARST, if there is a asynchronous reset. Then we do proc BFF for the flip-flops. Okay, what I'll do is I'll let you guys go and visualize the hierarchies after each of one of these using GraphViz in your own time today. We'll come back and explore that again from the perspective of some timing constraints and timing analysis in the next lectures. As I pointed out, we'll map into multiple libraries, we'll do the timing reports. So please be very, very fluent with this Yosis front-end flow. Sorry, the synthesis flow. Okay. Then after proc, who is going to tell me what are we supposed to do next? Sure. We want to do opt. So optimize. There are a couple of stages for opt. As we discussed already, we do the mux tree optimization. So opt mux tree, as you see, it tried to do certain mux tree optimizations and ended up with warning in some of them. And then we want to do opt clean to do further optimization. I think let's do proc and then do again opt clean. That's what warning was. And now it ran it cleanly. That is nice. Perfect. So we are able to do this. I'm not going into each one of these design hierarchies like we visualize. So every time, so let's just do show was the command we ran. Let's just do that. Show stretch this ALU. So after we have done this, our ALU would have optimized further. I have not gone and visualized that yet. Please go back and do that because I have given you all the commands. I've given you all the libraries. We will be doing extensively running the synthesis I point out again when we do the timing reports. So it will be useful then. Okay, so next, what is the next thing we want to do? Tech map. And after that, we would want to do PFF lib map, right? And the lib map we want to do is with a lib file. Where does that lib file exist? Let's try to find its path. Sorry, my bad. Okay, so let's try to find the path for that lib file. For me, it is located here, Sky 130A. This PDK is given to you. So please, Venkat, I did a proc again. So libs ref, So let's see, which library do I want? I want to say map it into this library. Okay, so first what I'll do is I will do pwd here. I will copy this path. Okay, and I paste it here. Then I go back, copy the library. Wrong thing. Okay, so now I've done the DFF libmap. Similar lines, what I can do is I can do the ABC libmap. ABC, let's just swap the previous command. Till now, I've only mapped the D flip-flops. ABC. Now it is mapping the whole thing. Let's just go and see the ALU once again. So now if you see what has happened is all of these ALUs are mapped into specific gates from the technology. See Sky 130, everything is in the Sky 130 technology now. ABC is a mapper, Rajesh. Sure. People are asking to go slower. Sure. Currently what all I'm doing is I'm asking you to go through the complete synthesis flow. So in the complete synthesis flow, what we did was we read the Verilog, we did a proc operation on them, we did an opt operation on them, then we did a tech map, DFF lib map, and the ABC lib map. So we are going through the stages one by one. The slides for different commands and stages we discussed already step by step slowly in the last lecture. That's why I was going a little slow. As I mentioned, the tool is we are going to get really hands-on. So do practice these things on your own and in the background. Otherwise, things will move a little fast because we want to capture a lot of the backend flow with you guys. So now a good question. So history of commands. Sure, I can show you the history of commands. So let's start with the first one. The first thing we did was we read the Verilog. We read the top Verilog. Then what I did was I did a proc ARST. And yes, I read the Verilog, make sure that I do it with the no latches tag on it. Otherwise, the latches are not mapped correctly. Then I did a proc ARST, proc ARST, then I did a proc DFF. Then I did a opt mux tree. Then I did opt clean. It was giving me some proc related warnings. It told me that please run proc again. Not everything has been done. So I ran proc again, and then I ran an opt clean again. After that, I did a tech map. After that, I did a DFF lib map. And after that, I did a ABC Liberty map. So ABC is basically a library mapper. It is a tool in itself which uses imports. After that, the only thing left to do is clean. There are 0 unused cells and unused wires. I did a clean on that. Mithul, we have already provided the steps in the last lecture. So last lecture, slides are already there, steps are already there, everything is already there. We are using literally the same commands we had in the last slides, yesterday's slides, and which are already uploaded. Okay, we did a clean, then we do a write Verilog. Let's say test synth EICT FTP serve.v. and it wrote a Verilog. We can go back and see if it came there. So we have our Verilog file over here. You can do more tests and this, and as you see, now we have a tech mapped Verilog file at our end. So you see all Sky 130 PDK, everything has been mapped, NORs, ALUs, everything has been mapped into Sky 130 muxes, everything is in Sky 130. So you have mapped everything into the PDK now. So the day 3 slides are not in the drive. Day 3 slides should be in the drive. I think I'll just confirm it with Firoza ma'am. I think those were delivered yesterday by me. So they should be there. If they're not there, I think E&ICT will do that today itself. They're not there. Sorry about that. Ankit, these commands are for uses only. Rajesh is asking ABC. ABC means all gates. Yes. DFF means only the D flip-flops. Okay, so the way we are going to proceed, I want everyone to go back, run these commands on their end, visualize the design on different stages like we did for the previous smaller files. Make sure you are able to run each and every stage of the flow correctly. Make sure you are able to map it to different lib files. Why? Because we will be doing that extensively and doing timing analysis on them. So please go back, do these. It's a humble request. Otherwise, you'll not be able to follow along with the rest of this course. It's a very, very hands-on heavy course going forward. Any more questions? And there are concerns with respect to open lane. We will sort out the open lane issues over the next 3 days. Which lib files to map to? Okay, perfect. Good question. So lib files, the lib files which we have provided you guys is the Sky 130A PDK. Please go and map this into this. This is the PDK where we want to, and this in this go to libs ref, go to Sky 130 FDSCHD. Here you have lib, and then map into lib files here. So yeah, I think this is all I had for the first session today. This is no, I see no more doubts here. Yes, timing constraints will be further integrated into this flow as we move along when we start doing the STA part of it. Yes, definitely. We are trying to build up slowly. Naveen will look into all those commands in the next few sessions for sure. Okay. What else? It's actually the other way around, Ankit. FF is used for hold usually, and SS is used for setup. Puneet will have a setup hold discussion with you on the STA, and that will be more clear then. Okay, I think we are moving along well. As I pointed out, the slides for today's lecture will be uploaded. The open lane issues will be sorted out over the next few days. And then we'll meet Monday and continue with the adding of these constraints, then switching over to the open lane flow to further analyze them. and doing more design and implementation flow there. So that's the general plan. Now Puneet will cover the rest of the IO files and less flow topics with you guys. I think, yeah, Firoza ma'am, I think we're good for the first session. We can probably take a few minutes break and then Puneet can follow along in the next one.
Hello.
Yes, ma'am.
Yeah, sure. We can have a 5 minutes of break. So next session we will start by 11:35. So next session will be taken by Punit sir. So I'm giving the sharing rights to Punit sir. I request Punit sir to please check whether you're able to share the screen or not in the platform. Okay, we can see your screen, sir. So thank you. So dear participants, we will resume from 11:35. Thank you.
Okay, good morning. Good morning, everyone. So I'm sure all of you are back. Yes or no? So you know the rules. Use a Q&A section and just write yes. Great. Okay, so we will start the session, the second half of today, and the whatever we have left yesterday, we're going to discuss that particular part. And basically the IO files, the input output files, whatever the files we needed. So I think yesterday when we were discussing, we discussed this .lib files, and I gave you an idea about the from the combinational cell point of view. So how many of you just check the files in the way in the sense? How many of you have just gone, open the files and just check it like, okay, what is inside that particular file? So if you have done, just write .lib. Just write .lib and don't write so long. Just write .lib. Very good. So Anant just mentioned .lib. That means Anant did it. Okay, great. So there are a couple of people, they are active. I think the rest of the people, they are just on a listening mode. How many participants? 372 participants. Okay. And only 7, not even the 7 responses. So that means very few people, they just checked it. That's all. Okay. How many of you have these files on your laptop or the desktop? Yeah, I think you guys can just write me. Okay. Mhm. Great. So again and again, me and Aditya are going to push you for this thing. So this is uh, like this is a workshop. This is something which is designed and delivered only for you guys. And if you want to use the maximum use of these type of workshops, then the thing is like you have to be active for the next 10 days. Like now it's just like after today, I think it is just 6 more days. Okay, so let's if you have gone through those files, let's try once again, and maybe I will just ask you a small one or two more question, and let me just see how many of you can answer. So yesterday when we just discussed something in these folders, lab, lib, ref, and the lib tech, and I think we were here somewhere. And after that, I ask you just to open any of this particular file. And out of this, we open a lab. Let me just see, okay, for which we did it. We did for this. No, but that's okay. So if you are in the lib directory, now in this lib directory, we will, let me just open this particular file, or maybe this file. Let me see. Yeah, okay. I'm going to open this file, and now I need some answers from you guys so that I will come to know like okay whether you guys have really checked this particular part properly or not. Okay. So let me ask a question. So how many of you have this folder structure with you? If you have, again, once again, so we were somewhere here, and then you can see this particular file. Can you guys just open this file on your terminal on your side? Yes or no? Just open it, and I need one small answer from all of you. And that is if you will search the cell, enter here. Maybe we can see whether okay, let's check this only. Can anyone just let me know how many input pins are here in this particular cell? If you guys have opened this file, okay, just open it. Let me tell you the path once again. So we were in the lib of what? It is a 130 FD SCHVL in this particular, and from where exactly you find this in the lib reference. So go in the lib reference, HVL, then lib, and then which file? It was a 5, this one. Just open this file. Okay. Now can you just tell me how many input pins are there for this file, this cell? I just want to check how many of you are attentive and how many of you actually have these files. So your answers are going to help me out, like, okay, whether you guys are attentive or not. Okay, so few are saying 3, some are saying 2, 5, 2, okay, 3, 5, very good. So whenever there are multiple answer of a particular question, that means it's good. It's good. It's good from my perspective, at least. It is not a copy paste, and even it looks to me like okay, people don't know a lot of things. That then only I can do my job. If people know everything, then I cannot do anything. So good. So now yes, the range started from 2, 3, 4, and 5. Now I think it's a input pins. How many input pins are there? Input pins, how you're going to figure out how many input pins are there. For that, you have to go in a pin. First, you have to search the pin, and then you have to just check the direction. And the direction, if it is written input, that means it's an input pin. And if in the direction it is written output, that's the output pin. So here we have A1 pin, that is the input. There is a A2, that is also input. Then B1, that is also input. Then that's all. X is the output. That means there are 3 input pin A1, B1, and A1, B1, and A2. So now if there are 3 input pin, now in the output pin section, which is X, this is output pin. You remember yesterday I have mentioned something related to the related pin, and I was just talking about certain input and output relationship. So I have mentioned like okay, there are the metrics. Those metrics are going to be in the output. in the output section. So this is a pin in from bracket started and is going to be closed, and they are going to certain metrics, and those metrics has a dependency. Those metrics have a dependency on the input pin. That means there is a relationship between the output and input pin. So what do you think in this particular matrix, how many in this particular section, basically pin X in that particular section, how many matrix is going to be there? Or you can say the related pin. If three input pins, that means three relationships supposed to be there. And how you're going to search it? For that, there is a syntax which is a related pin. And if you will search the related pin, it is with respect to the A1, with respect to then A2, then the third one is with respect to B1. That's all. It should be in that fashion only. Yes. And the same is going to be happen in the timing section. In a timing section, if you will see, if it is coming with output pin, the timing section, it is going to be in that way only. But here, actually, the reason I'm taking this particular example, because someone asked about the CCS file, and here you can see these are basically certain thing which is a CCS N files. I will show you one more file. So that is with respect to the general matrix, and here we are talking about the CCS thing. So someone asked like, okay, what is this CCS noise file? Someone said like, okay, what is the normal one? Let me see if I can show you some. Uh, so normal, I think it is not in this directory. It should be somewhere in. Let me just see. Yesterday we were trying this thing. Go on. Thing. Okay. I have to check it. That means 1 second, guys. Here, if you will see, it is more or less as a power timing. Yeah. So here in this particular file, you can see we are talking about the cell fall, cell rise. So when we are going to discuss this timing models, so we are not going. So first of all, we are not going to discuss too much in detail about the timing models as a theoretical side. But there are two type of timing models. So when I'm saying the two type of timing models, in the sense if you have input and output relationship. So yesterday I have mentioned that okay, in an input output relationship, the delay is one of the important thing, and you have to calculate the delay. Now the delay has a dependency over the certain parameters. Now how you're going to model your file so that once the tool is going to read that particular file, it will give you the exit delay number. So there are right now in the industry, there are two type of models which we are using. One is someone just mentioned very correctly. It's a composite current source model libraries. That means it's a current source based. So I'm sure like all of you know, we have in electronics, we have studied this thing, current source and the voltage source. So when you are when you are creating a model which is you have done using a voltage source, so it is basically the voltage related thing. Then we are talking about the NLDM, non-linear delay models. So yesterday I gave an idea about non-linear delay model, the piecewise relationship, and I have just mentioned like, okay, that's one of the way to calculate the delay. So this particular file which is in front of you right now, it is basically on the based on the NLDM models. NLDM models in the sense like you as an engineer, you said like, okay, these I'm going to create the input output relationship of a transistor as a on based on the voltage source, and then you came up with a matrix, and that matrix has a dependency over input transition, output load. So in that particular way you came up and you said like, okay, this is our model, and you gave that model as a name as a non-linear delay models, so NLDM libraries. So that means any library which has these type of modeling numbers, that is a NLDM library. Now, there is some other educational institute, some other university, some other scholars, they were also doing the analysis, but they use the approach of current source, and they came up certain formula, the matrix, and they said like, okay, with this particular formula, this particular matrix, if you are going to calculate, even in that particular case, you will get the same uh, result, in the sense the more, or maybe the more accurate, or maybe you can say you came up with that particular matrix or that particular things, the numbers you came up, and that is basically come up with this CCS library code, composite current source model files. So I think now you can understand, it all depends how you're going to model. Now, in that particular model, if we are going to model the noise also, so like in electronics, in a communication also, we study like, okay, uh, noise is a random noise, systematic noise. So there are different type of noise. So in our circuit also there is a noise, and now you said like, okay, I'm capable to model the noise also. And if you're going to model that particular noise, and then you come up with the library, then you will say like, okay, this is basically the noise library. Basically, through this particular library, we can in this particular library, basically we are modeling the noise also, or we have modeled the noise. Similarly, nowadays we have one more uh, one basically in a lower technology node, I would say, there are another thing you will see, that is a statistical STA related, that is a statistical based thing. So whatever the analysis we are doing till now, we are saying like, okay, my setup is the slack is this much. So you're saying like, okay, the way the tool is going to calculate, the tool is going to calculate in a very different way. So that's just a mathematics things we are talking about. And tool is, I will show you in next week. I will show you like, okay, what is the setup, hold, what is the meaning of STA, and how you're going to do that particular part on any design. So we are going to talk about that particular part in detail. But the reason I'm just talking about, you will see now on a Google or maybe somewhere, you will see people are talking about the statistical STA. Now, if they are talking about the statistical STA, that means when I'm doing the STA analysis at that particular time, I'm not talking in terms of the single number. Now I'm talking in terms of the statistics, and statistics that I'm sure like you guys can understand the meaning of the statistics. Statistics in the sense like out of 100 net 99 is giving you this result. If I will tell you in this particular way, like, okay, the same situation, everything is there, and the delay is this particular number. So that number is like, okay, if we are going to pass the same signal 100 times, then 99 times it is going to give you this number, and the one maybe something else. So now we were talking about statistics, and then all those uh, m- statistical mathematics come into the picture. Now, if the tool is going to give you that particular result, then obviously the modeling supposed to be happen in the similar fashion. The numbers which you are going to capture inside the library, that is supposed to be captured in that particular number. If you will just write one number, then how the tool will come to know? Like, okay, I have to do basically what is the statistics. If it is a single number for the tool, it is basically like, okay, all the 100 nets or 100 times it is going to give me the same result. So if we are talking about statistics, then you have to be in that particular, you have to model your libraries accordingly. So you will see in an advanced node, in a maybe in the research papers, you will see about the statistical STA also. So reason I'm just discussing this particular part because I mentioned yesterday also, my goal is not to just give you um, general idea like, okay, this is the way the people are working. I just want to uh, also tell you like, okay, these are the areas where you can do your research, or maybe you can do something different. And uh, from this thing whatever I have just discussed with you, now I'm sure you guys can think like, okay, there is a area, there is a field where you can do the research or the analysis, or something. If you want to publish a paper, you can talk in terms of the modeling of a particular cell. Now, the way you are going to model it, the way you are going to calculate the delay, now how you're going to model it, and how you're going to capture it in a textual form. So yesterday, my main focus was like, okay, what is in the .lib file, and how you can read those .lib files, how you can represent that particular the information in a .lib file. And I also mentioned, if you have a open source tool, then or if you have it, if you are developing a tool, how you can use these particular files. So the tool is basically programmed to read those syntax. Now, what about most of you people from the research? Most of you people, what you guys are doing? You're writing, you're doing a modeling, you're doing a lot of simulation. But right now, most of you have a dependency over the industry tool or the open source tool. But when it comes to the formula, when it comes to the equations, with the help of the equations, with the help of the maybe the MATLAB or something, you guys can do a lot of different simulation. But when it comes to the tool point of view, you become stuck. You are like, okay, we can't do anything. We cannot make any changes in the tool because you have a dependency over the tool. So this open source tool are going to help you there. If you have a little bit understanding about the C language, you can easily modify all these tools. So most of the tools are written either in the Perl, in the Tcl, or the C language, or some of the tools they are based on the Python also. So that means if you have a understanding about the C language, C++, or the Python or Tcl, you can modify these particular tools. It's just like you have to you have to open all the files, and you have to understand what basically the flow is. And if you can make the changes in those tools internal files, that means you can make sure like, okay, your tool behave or do the calculation, or maybe come up with a certain syntax also. So the point is, you can design your own .lib, maybe with your own syntax, your own models, your own numbers, and make sure like, okay, the same thing tool can understand. So just make certain changes in a tool so that you're not supposed to do all these things on a daily basis. So those who are good in a MATLAB, maybe they can see like, okay, how they have to just code that particular part in a tool. So that's the main purpose of these two sessions, yesterday and today. Like, okay, you guys should know what is written inside the file, what information is present in those files, what are the areas where you guys can work, and you guys can if you have to make certain changes in the tool, can you do that particular part? If you want to write your own uh, input files, can you do that particular thing or not? So that's the thing. So dotlib is one of the thing which most of the people think like, okay, if I will do some research, can I write this particular part myself? Yes, you can do that particular thing. And when it comes to the tool dependency, that's okay. I think that you can any point of a time you can remove that tool dependency, and for that this open source tools, that's going to help you a lot. Okay, so is it clear? Any question? I know, like, okay, if more research oriented part it was the discussion, but any question you have till now? So someone just asked like, okay, Anant asked, while do the timing analysis to calculate the delay which is used, rise or the fall value. So Anant, we will discuss about this particular part in detail, like, okay, how the tool behave and what calculation you should do. Okay, but the answer of your question is we are going to analyze using the rising value also, or the using the falling value also. So we are going to do the two analysis, like, okay, in a circuit, if it is a rising and if it is a fall, then things maybe so it's like in a circuit the starting point. If it is rising, then if it is falling later on, that is okay. That means it has a dependency over the previous stage. But if you will ask me in a complete circuit, we will do both the analysis. Okay. So you guys are alive or feeling sleepy? Because I can't see any response from anyone. Alive. Good. So you guys should be alive. Good. Very good. So one question, if we change the constraint from the SDC file, want to change the actual result. Okay. So answer of your question is, so SDC SDC is something. SDC file is basically the constraint file, and the constraint file as such supposed to be written by you only, because you have a good understanding about your design. You have a good understanding about the constraint. So think this constraint file as like if you have to travel from your home to the airport, or home to your maybe your office or the college. So you may have certain constraint. For example, your constraint is you cannot wake up early in the morning. That is your constraint. For someone, maybe the constraint is they don't have four-wheeler, so they have to travel using either the cab or the bus. So that's the constraint. And maybe the constraint is like your office has imposed certain constraint, or the college, like, okay, the college is start at 8:30, so you have to be there, you have to report there maybe 8:50 in the morning. So that become your constraint. So see the point which I'm just trying to make it here, like, in it is a design dependent, the application dependent basically. So if it is a design dependent, application dependent, then who's going to write that particular constraint, that the constraint, basically the constraint of my design, the person who know very well about the constraint, so that know very well about the design. So those people can write uh, the constraint. So now if you're saying if I'm going to change the constraint, when it changes the actual result, obviously it's going to change the actual result. But you're going to, if you're writing, if you're making certain changes, then I'm expecting like like why you are making those changes and how it is going to affect your design. Okay, great. Now let's talk some theoretical things and then we will come back. So yesterday we have discussed two things. One, the logical libraries and another is the physical libraries. Now there is a something known as the technology related libraries, technology dependent libraries. Now what is the meaning of a technology library? First we have to understand what is the technology we are talking about. So basically it is a foundry specific files, foundry specific data. So think in this way, you are going to fabricate your chip. Now, if you have idea, then there is a global foundry. That means there is a foundry name as that's the name of the company. It's a global foundry. There's the TSMC is one of the foundry. Then in India we have SCL Chandigarh. They have a foundry. There are few IITs. They have a very small foundries just for the testing purpose. They have a foundry setup, so foundry related setup, that means the fabrication setup, sorry. So they are doing each and everything, so that can be your foundry. It is XFab, that is the one of the foundry. So what is this foundry? Basically, if you're going to ask me on the layman language, it is all about it's a factory. It's all about the area, so company where you're going to fabricate your chips. So fabrication in the sense there are machines, there are materials, they have certain ways to fabricate that particular part. Now, when I'm saying the way, different ways in the sense, I'm not talking about the process that the oxidation, latch up, sorry, oxidation, lithography. I'm not talking about these processes. I'm just talking about the different ways in the sense maybe obviously they will have the different machines, they will have different engineers, they will have a different setup. Now on the basis of that, or maybe they have certain very specific technology also, on the basis of that they are going to give you certain recommendation, they are going to give you certain rules. They will say like, okay, if you want your chip supposed to be fabricated in my company, in my fabrication lab, then you have to follow certain rules, because I know my machine, I know my infrastructure, I know my technology very well. And if you want your chip supposed to be fabricated here, then if you are not going to follow certain rules, then we are not going to give you the guarantee like, okay, your chip is going to work properly or not. And as you go down in the lower technology node, these rules, these type of recommendation, that's going to increase a lot. Now, there are a lot of factors depending upon the type of a foundry and how they are going to provide you this particular data. So they usually provide you the data in the form of certain rule files, or maybe they will just give you the pictorial representation. So in terms of the pictures, in terms of the PDF, in terms of the maybe some videos, they will give you in that particular way. And they will say like, okay, you if you are so this is the way we usually fabricate the chip, and these are the places where the variations are going to be happen. And we are going to deposit the first layer of maybe X dielectric, after that the second dielectric of this particular layer. So I will show you one diagram, maybe that is going to give you an idea. But so point is, they are going to provide you all this information. Now, this information, if it is in a form of a doc, if in a form of a PDF, then how the tool is going to understand? Tool is not going to understand that particular part. So at least in VLSI industry, tools are not smart enough. They can do the image processing or the the text and everything, they can just read correctly. So what you have to do, you have to write in a text file. Now, again, when you are going to write another text file, then you have to make sure like your tool supposed to understand that particular text file. So what in our industry, what people are saying like, okay, so they have divided the whole ecosystem into three different category. One is a designer, and another is a tool provider, and the third is a foundry. So what usually happen, the two foundry are going to interact with the tool providers, or the tool providers are going to interact with the foundry, depending upon who's a industry leader, who's like bagger basically. So they are going to talk to the each other, and they will make sure like, okay, for the designer they will give you all these files in a text format. So as a designer, sometimes we think these files are coming from foundry. Sometimes we think these are coming for the tool provider, but actually, uh, logically, if you will ask me, these files supposed to be the part of the tool provider, because that tools should understand that particular syntax, and the tool provider should work with the foundry, and they should work and make sure like, okay, these files are prepared as per their process. So for you as a designer, it doesn't matter. It doesn't matter, but yes, the chip is your chip, so you should know what is the meaning of that particular file, what is written inside that particular file, what format is there, and sometime when we are doing the debugging that at that particular time, this is very important. Now, why I'm just giving you all this idea. Now, let us suppose you want to do certain simulation. You want to make sure like, okay, something is done. Now, in your lab, maybe in your institution, there is a small foundry. You have created your own foundry, and for that particular foundry, what are the different things you should know, and how you're going to capture it with respect to a particular tool. So I'm just giving you that particular flavor. So I just took a example of a one of the 32 nanometer technology. So basically, just few example, like you should know, you should have certain nomenclature so that the tool can understand like, okay, what is the name I'm talking about. So like here, NWell. So this NWell DNW. So basically, it is another nomenclature. It means deep NWell, the poly. This is a poly layer. This is a diffusion layer. Similarly, for the metal one, people can have a different nomenclature, like metal one. Here, if you will see the capital M, it can be is metal two. Means in terms of a metal, if you will see the small m, and then it can be the M1, M2, M3. It can be any nomenclature. Same via we represent in this particular way. Now, if there is a certain custom via, maybe you can just come up with some other name. There are something related to the design rule attributes like minimum weight. So this minimum weight, minimum spacing, and these things, if you know the process, if you know the foundry process, I'm sure you know there is a process, it is all related with the light, and there is a something in terms of wavelength, in terms of refraction, in terms of diffraction. Those concepts come into the picture. So what you guys have to understand this particular part, you have to just understand, you have to just go back, read certain articles, just see like, okay, how etching happen, how what is the lithography, what is the how we are going to decide the wavelength, what is the physics behind the fabrication. And once you will come to know about that particular part, it's going to be very easy for you to understand why we need a minimum width, why we have this particular rule. Actually, the purpose of this minimum width rule is like, if the wire don't have a minimum width, if it is a less than this, That means there are equal chances, like okay, your wire can become a open wire, or it is not going to work the way you want it to work. So usually foundry provide you like, okay, this is the minimum width, the spacing, default width, and then they have the recommendation also, like okay, if you are using a wire for clock, then the width should be more than this. That is a recommendation. Means from the foundry point of view, there is no problem in fabrication, but they are saying because it's a clock net, things should be different. That's something they will provide you in terms of the recommendation. Then once there is a layout, if you're going to provide that particular layout to your foundry, then how you're going to provide them? Are you going to provide them as a picture, or basically some format you have to provide, and the format which foundry can understand. So they are going to tell like, okay, we can understand when this layer is represented, like anvil supposed to be layer represented with the textual format in the binary, it's supposed to be the 48. So if that is the case, so they come up with something known as a layer number, the mask name, pitches, they come with respect to this thing. So all these information is a part of a tech file. So I will show you one of the tech file designed by someone which is compatible for the tool. So you can understand that that's the something you can design for your foundry also. Now see the snapshots, so the way people write it, or the you can see like, okay, it is written here, and again it is, you can easily understand like, okay, which technology we are talking about. Some 32 technology we are talking about. This is just a date, like at which particular date you have created this particular file, and then you can see some certain default values, and the units are there. Everything like everything like current, capacitance, resistance, inductance, temperature, they are talking about everything. Then then we are talking about layer by layer. So now if we are talking about the anvil layer, so in that particular anvil, what is the layer number, so that foundry can understand like, okay, which what exactly you're talking about. What is a mask name? So if they will name it, then the way they are going to name it, they just name it as a anvil. And then whether visible, selectable. Now this portion, visible, selectable, blink, color, this is basically the tool dependent. So when you are going to use this technology file within your tool, so like in our case, if you're going to use it for the magic, so I will show you in the magic, like, okay, uh, when you are going to pull a technology file. So basically for the magic, it is magic basically one of the layout tool. It is going to tell you like, okay, in this particular fashion, your anvil is going to looks like. So now for the anvil, there are two things. One is how you are going to represent, and the second is where you are going to represent. So in how you're going to represent, that means whether it is going to be a red color, green color, blue color, and or it is a solid fill, or it is a something like a check. So how you're going to represent in a layout in which particular color, that's the one way. That's just for the tool purpose. The second thing is where you're going to represent it. That means how you're going to draw it, basically, where exactly you're going to draw it. So one file is providing you the information about the physical location, physical information. The second file, which is I'm talking about right now, the technology file. In that particular technology file, it is going to tell you about the technology related thing, plus certain properties, or you can say it's going to tell you the properties of that particular layer. Like here, we are talking about the color. There's something which is uh, one of the visual related property, and then there are certain numbers like default width, minimum spacing. This is something which is related to the technology, like, okay, if you're going to draw the layer less than this width, then it is going to create a problem in your in your fabrication. So for that, we have a in our flow, there is a stage, there is a step, basically I would say it's a DRC, design rule check. So design rule we are going to check, and these are the fabrication design rules, and those fabrication design rules we are going to check. So this technology file also help us in that particular way. So tool has inbuilt check capability, like okay whether they are going to check this particular part or not. So like I gave an example of some layer, then similarly in the metal one layer, and then for the metal one, so here see I just highlighted very clearly, this is a layout attribute, this is a display attribute, this is a design rule attribute, these are the design rule attribute, and then these are some other property of that particular layer, which if you remember yesterday we were talking about certain the capacitance related thing. So if you have to calculate the capacitance, if you have to calculate the resistance of that particular layer, now that capacitance, that resistance, it will have certain dependency over the foundry. So well, if you remember yesterday we were talking about fast, fast, slow, slow. That is on a transistor level I was talking about. But in a similarly, there are certain uh, variations in the layers also. So these type of layers, like in a metal one. So variation in the sense you are expecting foundry to give you or not the give you. You are expecting to from the foundry like they are going to fabricate a layer with maybe 10 micron. But like I said, every foundry they have certain technology, they have certain machines, and whenever we are talking about certain machines, then we have to understand like okay, every machine, everything has certain precision. Like they can be they can draw a particular line, but with a certain precision. Now if that precision is 0.00001 nanometer, even in that case, after that one it can be 1.4, 1.3, 1.2, or maybe it is a 1.5 also. So it all depends like okay, what is the precision of that particular machine, and that's the variation we have foundry supposed to tell you. See, they will tell you like, okay, this is the variation. It can happen. So my precision of my machine is this thing. Now, if that variation is going to be happen, then how it is going to affect your capacitance and resistance, how that's going to affect the current carrying capability. So all these information from the foundry side, they should provide you. So that's the something like here they just capture it like okay, if this is the dimension, this is a threshold parallel, and this is the spacing. So in this particular way, there are a lot of other rules also that's a part of a technology file. So just to give you an idea so that you can visualize whatever I was saying uh, in a pictorial format. I just want you to visualize that particular part because it's very difficult to visualize it because the in a chip you cannot just cut the chip and you can just see all these layers. But in our or in the layout also we usually see the top view of that particular layout. Now, if you have to see the cross section, first you have to understand from the visualization point of view like okay, how you're going to how it looks like, how the layer. So I just took one example so that you can visualize this particular part. So let us suppose this is your substrate and this is your poly. Now this is, first of all, this is not a top view, so you will not, don't think like okay, from the top you are seeing the metal and the poly like this. No. So this is basically the cross-sectional view. That means this is a substrate. On that particular substrate, there are going to be a certain dielectric here, and then you are going to have certain poly layer here, then dielectric and the metal is here. So right now I'm just talking in terms of the vertical things. I'm just talking in terms of like, okay, if there is no dielectric here, if there is no medium here, then you cannot deposit. You cannot deposit this metal wire here. It is not there is any pillar is here. So our construction, generally we do the construction, the first floor, second floor, third floor. You cannot say like, okay, after the first floor there is nothing, there is a complete air, and you have the third floor. Second floor is in air. You cannot do that thing. Either you should have pillars, or maybe you have certain empty, or maybe you can say the I just everything is like cemented. The second floor as such is just like full of something, but you cannot have that particular part. So it's just visualized in the vertical thing. So substrate poly metal one, and then foundry said like, okay, I need this much of minimum space, or you can say the height between the substrate and poly. Now, why? Question come why? It's because if you will just go back and see the CMOS theory, then we always talk about certain distance between the poly and the substrate. Now, because of n number of reasons, and that space is basically here, certain dielectric will come. So that the CMOS we have this TOX between the poly, that the gate and the substrate, the that our N-well or the P-well, N-well or P-well thing. So maybe it is all about that particular dielectric. So I'm just giving an idea. You can just visualize in that particular way. And then after poly, or if you want to connect that particular gate with a certain metal layer, then obviously you have to do it with the help of certain contact. So here, if you don't want to do it, then there's going to be the dielectric. So in that particular way, this thing is there. Now, question come, how Foundry is going to give you and how you're going to write it in a technology file. So Foundry is going to give you this data in this particular fashion. Now, if they will give you in this particular fashion, and if you want to write it, and if you want to just do certain things, so one of the like parasitic extraction tool, because parasitic extraction tool has to extract the capacitance. So what you can do in your technology file, maybe you can use this particular syntax. So the way I have written it is my own syntax. So this syntax is nothing. You cannot say like, okay, this syntax is compatible with any of the tool available in the market. This is my syntax. Conductor metal one minimum width equals to 0.3, minimum spacing 0.3. Now, what is 0.3? What is the unit of this? Obviously, I have to define somewhere. So in that particular file at the top, I can define that 0.3. So now this is the way I have mentioned it. So you can see for the metal one, I just mentioned minimum width is a zero point 0.3, spacing 0.3, thickness I specified is a 0.7. Then I have specified the height. Now height with respect to the substrate or with respect to the poly, that depends on me how I want to represent it. But the way I'm going to represent it, I have to make sure my tool should be able to understand in that particular way. So in my current, uh, the current this structure, I, I just consider like, okay, this height I'm going to consider with the substrate, because the substrate we usually consider as a ground. So if I have to calculate the capacitance of metal one, then this is the metal one plate. This is going to be a ground. So I have to calculate this distance. Then only I come to know no, that what is the first plate and the second plate. So this is a 1.4. How I'm going to calculate the 1.4? 0.6, 0.4, 0.4. So just add it, it become 1.4. Similarly, some resistivity. What is the material of this? That's something I know. I know in the sense the foundry is going to tell you like, okay, metal one will have this much of resistivity. The material which we are going to use it will have this much of resistivity. So that's the something we are going to tell here. So this is our syntax. Similarly, you can have a poly syntax. So the way I have just mentioned these syntax, similarly I can have the syntax for the dielectrics also. So this is all about the dielectric, like, okay, what is inside the dielectric, the way I'm going to uh, capture this thing. Don't ask me what is a conformal, what is a conformal yes or conformal no, because that's a completely different thing. But I'm just giving you the idea, like, okay, in this particular way, you can also design your own uh, technology file. One other sample, in this particular sample, if you will see, this is with respect to the foundry, and this is with respect to one of the industry standard tool, and this is basically from the synopsis side. So for the synopsis, this is the case. Just 1 second, guys. Okay, so in the meantime, any one of you have any question? Let me just see. All of you are available. Okay, so someone was asking, will all the metal layers have different resistivity? So good question, Aparna. So answer of your question is no, and another answer is yes. So it depends. So, but your question is good. So it's like a similar type of question. If you're going to ask the foundry, then the foundry will tell you like, okay, see, Aparna, it depends what all metals, what all different layers you are going to use. So we are going to tell you like, okay, which we will give you certain recommendation. So what Foundry is doing nowadays, because there are a lot of people like Aparna, and if Foundry will tell like, okay, yes, the resistivity is same, then they can say like, okay, we have done the research, and on the basis of that, if you are going to use this particular material, it will help me a lot. And somehow Foundry agree. So now for Aparna, there is going to be the one type of material, though for maybe for me it's another type of material. So what is happening nowadays, the founder is going to give you a lot of options. I think 50 60 different options are there, and that is known as a stack. So metal stack. So they use the terminology metal stack and metal stack, STACK. That means, and they will tell you like, okay, in this particular metal stack you can choose the layers, like, okay, this type of layer you want to choose it. That means with a different resistivity, with a different property, you can choose it, and accordingly you can come up with your design like, okay, I want to use this particular stack, I want to use this particular uh, combination of the metals. And that's the reason this technology file is not a one file. This technology file has a dependency over the number of metals. This technology file has a dependency of the type of the metals. So number of the metals and the type of the metals, different technology files will be there. I think I've answered your question, Aparna. Okay, one more question. Kind request, dielectric constant definition, uses, purpose. Thank you. So basically, in dielectric, you so like I said, there is a so just take this example, this pictorial view. I think this is going to help you a lot. This is the picture which Foundry gave you. Like, okay, in they have a technology, in that particular technology, they said like, okay, this is going to the Foxy. So they are saying this is the name, Foxy. Then there's a Fox B. Now in this particular Fox B, in this particular dielectric, they are saying there is going to be the OD layer, that is a diffusion layer. So that means the diffusion, that P diffusion, N diffusion, which we are doing as a MOS fabrication at that particular time, the N plus plus or the P plus plus, that's the diffusion I'm talking about. So they are saying like, okay, in this particular place, we are going to use this OD layer. That means before this, there is going to be a dielectric. Here, there is a diffusion. Now, the place where you're going to use this diffusion, that is okay. Rest of the place they are going to use this particular Fox-B. That's again going to use, they are going to use another dielectric, because you're not going to fabricate everywhere only a simple just the diffusion. You're not going to do in that particular way. So they're saying like, okay, wherever you want to use OD, you just use OD. Rest of the place you have to use this particular dielectric. Then this GOX, they said like, okay, this is the gate oxide layer. That means uh, after this, they are going to use this GOX dielectric, and then FOX layer. And then they said if there is any gate poly, if you're talking about, you have to deposit from here only. Now, this is the structure. This is the way they said, okay, I'm going to fabricate. So for the metal layer, you define it. For the diffusion, you define it. But for the dielectric, if you're not going to define it, how the tool will come to know, how the tool is going to be understanding, okay, what is the height of the dielectric? Now, what is the dielectric constant of the dielectric? Because you're changing the dielectric constant. Maybe say this Fox, C, B, A, all these dielectrics, ILDC, ILDB, they have the different dielectric constant. So to give an idea to the tool, like, okay, this is the dielectric we are talking about. This is the thickness from this place to this place. This is going to be my dielectric. And when you are going to do the capacitive calculation, then you know C equals to epsilon A by D, and the epsilon is a dielectric constant between the two plates. So that's the reason you should have a definition of the dielectrics, because if you will not have the definition of the dielectric, then that is going to create means you cannot do the proper calculation. Now, next question is standard cell in the library is written by constraint data in the ITF files. Okay, TF file, sorry. So now this is again a very good question. Now, but I will just put it in a different way. So now question is, in a .lib, I have certain data. In ITF, in a technology file, I have certain data. Now, how you're going to relate it? Relate in the sense, .lib and this technology file, are they correlated with each other, or can I do the can I without technology file, can I do something as a characterization? So think in this way: what the information which is present in your .lib file, that is basically coming after the characterization of your schematic. Now, schematic in the sense, in the schematic, you are talking about the PMOS and the NMOS. That means you're doing a simulation like, okay, in my NMOS, the current is going to be flow. Now, how you are going to check what is the current rating? It is the way you are going to model your NMOS or the PMOS. And model in the sense a NMOS, if you're going to model that particular NMOS, so on the basis of certain parameters in terms of the gate oxide, in terms of the threshold voltage, in terms of the VDD, VSS, in terms of the concentration, so all the semiconductor theory, all the semiconductor devices, all the equations which we have studied in those particular books, basically on the basis of that you are going to model a NMOS. So BSIM model, BSIM 1, 2, 3, 4, these are basically the modeling of a MOS. Now when you are going to model your MOS, that in that there are certain parameters that has a dependency over the technology, or that has a dependency over the foundry, like, okay, what doping concentration they are going to use, okay, what is going to be the dielectric constant. So maybe there may be certain parameter with respect to the dielectric constant, the threshold value. So that means if you're going to model it, you have to work with the foundry. And if you will work with the foundry only, then you will come to know like, okay, this is the model of my NMOS. So when we do this simulation, we should have these information. So in the simulation, there is a basically the model files. And those model, if you're going to change the model files, then Model files in the sense you will see in the simulation there is a fast, slow model files. There are the different model files. That means that particular model file is representing one type of a NMOS, one type of a PMOS. So now if the foundry is telling you like, okay, I can design the 5 different type of NMOS in a 130 nanometer technology. So you should know like, okay, all those 5 different type of NMOS, how I'm going to do the simulation. And on the basis of that, you are going to create your circuit. You're going to do the simulation. That means minimum 5 different type of uh, inverter you can create. Now, if the founder is saying 5 type of inverter, 5 type of NMOS and 5 type of PMOS, then that means it's a combination. Now, you can come up, you can say like, okay, I'm going to try 25 different combination, maybe. So that means you are now we are talking about the 25 different combination you can use for an inverter. That means there are the 25 different type of inverters when you are going to do the simulation. And once you're going to do the simulation, whatever the delay and all other results, whatever the numbers are coming, if it looks to you like, okay, you want to represent that thing as a part of a dot lib, you're going to do that thing. I think I answered your question, Satvik, if I pronounce your name correctly. The relationship between the dot lib and the technology file. Okay, great. Now, someone just asked, Foundry will give this type of picture. Yes. Then later we write the tech file. Yes. Sir, I'm a research scholar. Please suggest me the tool suitable for my research on the network on chip. Okay. The the answer of this question, I don't know. So this is not my area. Just check with your guide. Maybe he can help you out. Can we choose a particular metal layer only for the clock distribution? Answer is yes. Yes, if you're going to route only for a single metal, then you can do that particular part. Do we have to consider a foundry before working over on technology file? Good. Yes. It's a very good question. Like, okay, uh, before working on technology file, should we consider the foundry? Yes, obviously. If you don't know the foundry, then how you're going to write your own technology file? So maybe you can write the syntax, but obviously, if you're talking about some foundry, then you have to take certain reference, or you should know like, okay, what exactly you're doing. It's just like in the example, from the example point of view, I would say if you want to uh, uh, basically if you want to design a some application, let's take in a very different example. If you want to design a furniture, so and if you want to design it, then you should know like, okay, that particular furniture you're designing standard furniture. That means anyone can going to use that particular furniture, or you want to do it for the certain application. So for what application you want to design it? So it's that in that particular way it is related, like in a foundry and the technology file. Then someone is asking, will we do a physical design hands-on on this course? Like, yes, we are going to do it. That's the RTL2GDS. We will do it. Like today, Aditya gave an idea about the synthesis. Now, the next week we are going to talk about the floor plan placement. But everything is going to be happen on the open source tool. So, good question. Should we choose a different metal layer only for the clock placement? Does it need to be the upper metal layer like about 10 or 20? Okay, so uh, this question is completely different. Maybe we are going to discuss this particular part during the routing time. Sorry, that top metal layer, bottom metal layer, all these things we will discuss later on. Okay, then someone was asking some question around this syntax we will discuss. Just give me some time. Will the tool accept if we write own fabrication rule? So, Venkata Reddy, if you will write your own fabrication rule, tool will accept. Uh, hmm, uh, how should I tell you? So, are you going to use the same syntax which tool can understand? If that's the right thing, then no problem. Okay. So it's not like so there are so think in this way, you're driving a car and you're saying like, okay, as per my rule book, if the in the fifth gear it's supposed to be the first gear. So if you're saying my rule book is saying the first gear is on the fifth gear, but for that either you have to change the your car, basically internal structure of the car you have to change. So that's the one way. But if you will say like, okay, in my rule book, if I have to go reverse, then I'm going to use this particular R gear. So maybe they were talking about something else, they may be using the nomenclature in some other way, and you are using a nomenclature in some other way. That is okay. That is okay still, but you have to map that particular part. So the point is, if you're going to write your own fabrication rule, at least tool should understand that particular part. Now, if you're saying tool will accept it or not, if it is open source, no one is going to stop you. If it is something, some vendor, then maybe you have to tell them like, okay, integrate this thing in your tool. So people are working a lot with the design companies, at least the tool vendors, so they do this particular part. So I think Naveen was asking a big question like, okay, how to choose different matter layers and roles in the purpose. Please clarify. It is going to take a lot of time, but if we will talk in terms of routing, maybe I will just give you some idea. Sir, can we have both FinFET, MOSFET in the technology file? Yes, you can have. Sir, we include both FinFET in the same. Okay, same question two times. Sir, I can't install the pick 3 and okay, come on, why you're asking this question to me? Okay, so now let's come back. So this is one of the snapshot. In this particular snapshot, the reason I want to show you, it is like this is the one of the syntax which Synopsys decided, and they said like, okay, I'm going to write in this particular way. What is the syntax? You can see dielectric. Wherever there is a dielectric, they will say like write a dielectric. So if you will write it as a dielectric in a small letter, the tool is not going to understand. The tool going to understand if it is written in the capital letter. Let us suppose that's the way they have designed it. Now, or if you will just write a die, or die. So tool is not going to understand. So tool ni is going to understand when it is a complete this form, then a space, and then the name of the dialectic, and then within a curly bracket. So everything is defined within the curly bracket. If you have written thickness equals to 0.2, that means it's a thickness 0.2. So you have to write the thickness in this particular way only. Then you have to say equals to, and then you have to say 0.2. Now, if you will remove this equals to from here, then it become a something else. So for the tool thickness, nothing is specified, and it is going to give you an error when it is going to read it. ER represent the dielectric constant. So if you are thinking like, okay, I will just write dielectric constant here, it's not going to work out. Now you will see, I'm not going to explain this particular part like, okay, how things are there, but the way structure is there, this particular file is defined on the basis of this. So that means if if you are going to ask me like, okay, Puneet, you have this structure, write this ITF file. So if I have a good understanding, which I have, so with the help of this particular structure, with the help of this particular picture, I can write this particular file. Or if you will say like, okay, Puneet, we don't have this, but I have this file. Can you draw this? Yes, I can draw this particular part also. So just by seeing this particular file, I can easily tell you, like, okay, I can easily draw this particular file. So that's the understanding I have. And that's the same understanding you have to give to the tool also. So usually what engineers are doing, Foundry is going to give you something like this. With this particular picture, the tool provider, they have to come up with these type of file. So few are saying it is ITF file, few are saying it is a ICT files, few are saying it's a tech file. They just come up with these type of files. And these files tool can easily understand. And the files are written in such a way like, okay, that if within the tool, if you want to read these files, and if you want the tool to draw these type of diagrams, tool can do it easily, very easily. So every tool, whether it is a Synopsys, Cadence, or anything, so they have some side feature, I would say, apart from whatever they are doing, that pictorial view of this particular file. Obviously this is the 2D representation, this is a 2D file, but if the Foundry is going to give you something which is a 3D, and usually Foundry usually provide with in terms of a 3D only. So in that particular case, you should have all the syntax in such a way that you just explain everything. It's a 2D and the 3D, everything you just explain here in this particular file. So this is basically the technology file. We are not going to discuss this particular file in detail. So this is the same snapshot, but yeah, this is a more professional snapshot here. Now, there's a one more question. Like, okay, if you have some layer numbers. So here we were talking about certain layer numbers. See, here we are talking about the M7. So now you are using a two different tools, or maybe like I mentioned yesterday. So two different engineers, they came up with the two different tools. But in one tool, they were saying it's a metal one. In another tool, they said like, okay, it is a M1. How you're going to specify, how you're going to make sure like, okay, things are mapped correctly. So for that, there is a mapping file. So every, no, mostly, I'm not going to talk about the every tool because now we are talking about the open source tool. But yes, in terms of in terms of professional tools, they usually provide the mapping files because there the engineers are different. It's a big organization and they don't want any confusion. So they come up with the concept of this mapping file. That means between the two tools, if the same metal layer is just removing here and there, obviously it's going to be happen. Then at least from the tool point of view, they should not be confused, or you should not be like, okay, there are two input files, one for the tool X, one for the tool Y, and then later on you are just thinking like, okay, in a file one there is a the names are written as a M1, in the file two the name is written as a metal one. So let us suppose if you have just written that particular part, and later on you have just realized like, okay, this is the biggest problem. Okay, now I have to mix both the files compatible. That means both the files should have the same name. And then you did it. That's not a problem. But the problem come with the tool point of view. One thing the tool can understand, the other thing the tool is going to be understand the metal one, and the one tool is understand the M1. So if that is the case, then it's a big problem for you as a designer or you as a researcher also. So for that, the concept is a mapping file. So mapping file will be there. It is going to be mapped the two different files in this particular fashion, so that even if you have written design two different kind of files, two different files by the two separate people, but and they have used a two different nomenclature. At least you can map that particular part. Okay, so this is just to give you an idea, like okay, in a tech file, some mapping file, an ITF file, how things are mapped. So same thing, whatever I've just explained, is the same fashion. Like okay, you can just file it and you can just mark it in any way. So this is just give you an idea, like okay, how things happen. Okay, so I think this is one of the last one for the from the input output data files point of view. But still, let me just check it. Okay, so one more request. Question relevance and the role and the importance of TF role in the DRC, LVS, XRC stage. Please clarify. Okay, this is the request. Miss request means I can say no, I can say yes. So answer is I will check, I will see. Many times it happened that a company used tools from different vendors like the Synopsys, Cadence, or the Mentor Graphics. So can these tools be compatible to each other? No. So these tools, most of the time, these tools, even if these tools are not compatible, so we don't want the tools to be compatible. What we want, like the output of one tool can be uh, can be understood basically by the other tool. So if you're giving the output of a one tool as an input of the other tool, whether it is the same vendor or if it is a from the different vendor, so your intention is it should understand it in the same fashion, the way it was written and the way it's supposed to be read. It should not be like you are speaking in Russian language and I'm speaking in a some Gujarati language. Obviously, whatever you're going to speak, I cannot means you are speaking in the Russian language and I can understand only Gujarati language. So for that, what you have to do, either you have to come up with some person who can just convert that particular language, or maybe you have to use a translator, Google Translator, or maybe you can say like, okay, see, I cannot understand Russian. So I can say I cannot understand Russian. So let's come up with a common language, and that's the English language. You just speak in English, I can understand in English. So in the same fashion in our tool, in our semiconductor industry also, so every country, every vendor, they have their own language. That means they have their own way to write out the result. That is their own way. So their own tool can understand their own language. Yes. So if you have a data, if you are going to design something within the Russia, then you can speak the Russian language, no problem. And if I'm going to design something in India, and if I can understand the Gujarati language, I will do in that particular way. But whenever you are going to switch from Synopsys to the Cadence, then you we have to force. I'm going to tell you, or maybe as a designer, you have to tell the Synopsys like, okay, see, your tool should be able to write something in a uh, compatible language. So there are some languages, some database which is a IEEE standard, and some are like open access database. Means anyone can write, anyone can read that particular file, that particular data. So then it is basically the compatible in that particular way. Okay, I think I have answered your question. Okay, now come back. So till now we have discussed the technology file, we have discussed the logical files, we have discussed the physical files. Now the last one is a netlist file. So netlist is very easy. Basically, it is going to tell you the connectivity of all the standard cells, macros. It is going to give you the logical connectivity. It contains the nets. It is if you're going to use it, it is basically more or less as a uh, that fly lines related thing. So a Verilog netlist. So just to give you an idea, like okay, this is something, the Verilog language. Then this is also a Verilog language, and Aditya already gave an idea, like okay, how you can map it in your design. So if you have a design, if you have certain input pins, then where exactly you're going to map it, output pins, what are the data lines in the clock, and all other things. So these are basically from the box. Yes, from the design schematic, or the maybe the in the box format, how you're going to map it, that we have already discussed that particular part. Okay, now same. This is all about the syntax of the Verilog netlist. Then there is a something also known as a spice netlist. So it is basically the spice format. I think these are the something which you can just do the Google and you can figure out. Like, okay, what is a Verilog netlist? What is the syntax of Verilog? What is the syntax of spice netlist? So here we are talking about the sub circuit, then we are talking about the AND gate, output, then we are talking about the pin, then the ground, and the A. Basically, this is the format, and then we are talking about like okay, in this how many registers are transistors are there, like M0, M1, M2, M3, M4, M5. We are talking about the five different transistors, and then what is the width, what is the width of the PFET, similarly for the NFET, what is the width, and then the length, and then the diffusion and all other things that is here. So I think from the standard cell point of view, this is one of the sub-circuit definition. So it's like how you're going to represent your inverter into a textual file. Till now, it was like schematic is there. We were talking about the dot lib. Dot lib is there, that is going to tell the property in terms of the timing power. That is a dot lib. Physical, you can tell me in terms of the coordinates, like okay, from here to here the PFET is present. But when it comes to the model of that particular file, then that is going to be uh, the spice netlist you are just talking about. Like okay, this is a circuit. Now per PFET, what is going to the different property that you will find in a model file, or maybe you can represent here up to a certain limit. So in a sub circuit, we can write only those parameter which is a design specific, not the parameter which is like not technology specific. So technology specific, we are going to write in a separate model files. We are going to model the PFET. Now here we have written those parameter which is basically which can be added, which are editable, and the designers can change those parameters. So just try to understand the way I'm just giving an idea, like okay, where exactly the different files, different information is present. So this is all about the sub-circuit portion. There are certain files which is the timing related, and we will discuss that particular file in detail in our follow-up sessions when we are going to talk about the timing, different timing related thing also. But before that, let me just show you certain files in an ITF format, if I can just show you so that you will be able to understand like okay, what we are talking about, what exactly you're going to use it. So text file. So this is a one of the Skywater PDK, and this is the text file they just mentioned. And and the sorry, this is not a text file. Basically, it's a technology left. It's a technology left. So yesterday we were talking about the physical file. So this is that particular file. You can see here we are talking about all those size. We are talking about the coordinates, and we are talking about the pitch, offset. We're also talking about certain width related thing, but apart from that, means some rules basically, some technology specific rules. And then these are the different syntax are there. So what I'm going to recommend you just go and just open these files, then only you will come to know what is written there. Let me just see if I can show you one text file also. So let me go back. here. Want to see the tech. See if it is here. This is the same tech left. Okay, let me try this. Sorry. This is the magic related files. That's definitely you cannot see. I missed that file. I have seen that file where it is written. Okay, no problem. Maybe some other time I will show you. Maybe the next week when we are going to discuss all these files in detail. Spice file, I think that's something is there that you can see. So it is like every node, everything they are going to present. Okay, this is again one of the file where it is basically the RC magic RC file, but yes, it is basically the script file. But when you are going to read it, then I will tell you like okay, then you will come to know a lot of things. Okay. So this is that particular tech file which I was talking about, the technology file. So you can see it is a technology file, but here the syntax is completely different. So here they were talking about the diffusion, and then they are talking about this particular part. Like again, this is a technology specific. Here also they have mentioned layer and PC. So this is basically the technology related information, how you're going to map it. So I think you guys should check these files and you guys should understand like, okay, what is written here. Once you will read it, then only you will come to know. Where are you guys? Okay. Any question? Anything? So you can see like okay, you have to download these things, and it is already uploaded in your Drive box. Any question, guys? Yes or no? Today's session is a more theoretical or it's not interesting or what? No one is responding. Everyone is sleeping. Is it? Come on, guys. At least just respond. I know a lot of theory. So Devanshu, this is something sometime you need to know. Yeah, I mean maybe sometime maybe you know other people they don't know. So how to open these files? So in my system, I just double click and it's opening. But if it is not opening in your case, then you just use it open with any notepad. That's all. You just open it with any notepad. Uh, uh, then you can see. Show the path. Show the path of what? I think you have. So do you have the Google Drive link? If you have the Google Drive link, then you can download from there all these files. In the morning, Aditya also give an idea like, okay, what to do, from where to you're supposed to do it. Okay, so this is the good question. I'm running out of the memory after downloading all the skylifts and the design files. That's our zip. Okay, so maybe I will request EICT Academy, like from the next time they are going to shape one big, maybe 1 TB hard disk to all of you guys. Come on, guys, you are just asking these type of questions, or it doesn't make sense. If it is, obviously it is a big, then it's going to be out of memory. Then clean up your hard disk. Okay, now let's talk about. I got it. People are like they they are just like, okay, finish this session ASAP. So I will do it. So maybe just couple of few slides. Timing related SDC is a timing constraint, clock definition. So there are two type of usually I divide the files in the two category. One is having the delay information related to the net, and another one which is having a delay information related to the cell. So net delay information we can have in a SDF, which is a delay format file, standard delay format file. It's very standard. I would say the syntax standard in the sense very easy to understand. So this is just a snapshot, and after that you can just write in this particular fashion. So now you can see different files have a different syntax, and it's because different tool have because these files are going to be used by the different tools and different stages. So and the tools are different, stages are different, the syntax can be different. So here the syntax is different. It is a SDF file, the syntax is there. Here you can see they are talking about the cell type, the delay type, what is the absolute. So if you are going to understand this SDF file, just do the Google SDF uh, document or something, IEEE standard. So you will get the complete guide for the SDF. See, it is in a cell instance, everything is in this particular way. Then the second is a net delay for the SPEF file, that is one of the parasitic extracted file. Okay, here we usually have RNC information. So here we are not talking about the delay of a net directly. Here we are talking about the RNC, and with the help of a RNC, you are going to calculate. You in the sense the tool is going to calculate the delay value. So for the net, then again, that net you're going to model into the R and C, that is a pi model, T model, and on the basis of that, you're going to solve it. And then, this delay of a net, if for the signal, it is like uh, they usually calculate with this TR, TF. So in the books, if you will go and if you will see what is the delay, they will say the tau, and that is related to the RC, and that means the resistance and the capacitance. So this is something like if you want to calculate the delay, you have to calculate RNC. For that RNC, there is a parasitic extraction tool. They will provide you RNC, and then tool is going to calculate the delay. So that means technology related information is required to do the timing analysis. Then this is a wire load model. This is a approximate analysis. And just right now I have mentioned you need a technology related information if you want to capture RNC of any circuit. But if you don't have RNC, you're very early in the design, like just after the synthesis. Just after the synthesis, if you have to calculate, the uh, delay. So just with the help of the RNC, you can do it. But if you don't have RNC, then how you're going to do it? So for that particular portion, we have this wire load model. So this is basically the approximate number, and it will give you some numbers, some delay numbers, some R or C numbers. Uh, they may not be accurate, but they are uh, I would say very close to the accurate number. So that's a part of wire load model. So SPEF, this is a syntax. Best is do the Google, you will figure out the syntax. Wire load file, this is a syntax. Again, best is do the Google and you will figure out the syntax. So these are a couple of design constraint things like in a design rule, max trans, min cap. We will discuss this thing later on. What is the importance of this? But these are also the design constraint files related to the design constraint, and you will see this particular part. So remember, in a dot lab, you can see the max cap, max fan out. This is related to this particular. These are the constraint for your design. Now timing constraint. So again, SDC file is there. So this is the portion which is in SDC. Aditya already explained you a couple of things in the today's session also. This is a physical constraint, like you are saying, this is the size of my chip, and so that means everything you have to define within that particular size. So that's part of physical constraint. Then yes, it's just like shape of shape of a net. This is also the part of physical constraint in terms of the coordinates. Done. So this covers all the IO files, input output files. Now, if you have any question, just let me know. Else we can close this session for today. Okay, so someone is asking about in synthesis, we use map command. Is it related to the tag file? That's design is map. No. It's not design is going to be mapped with a particular technology. It is like within the synthesis, there is a uh, basically there you will have a .lib files, and you want to map your gate with those .lib files. So that map is basically related to that thing. Okay, then someone saying so, okay, slice and all. Then Naveen is saying kindly request regarding yesterday's session. Kindly regarding filters, antenna rules, routing task, lockage, sync. So Naveen, I will see what best I can do as a part of this particular course. Okay, can you send my PPT? Yes, I think that's going to be uploaded soon on the your sharing drive. I'm using the Genesis for synthesis. Okay, so you are using the industrial tool. Okay, I think that should be okay. Does the same as DC command for uses? I think it's same. So it's going to be same file because they are also using the same syntax. So that maybe you can just source it. You will come to know that whether it's the same or the different one. Okay. Okay, great. So no question, nothing. I'm good. Firuza ma'am, maybe we can close the session for today. or if any one of you have any question related to the anything with your attendance and all, maybe Firozaman can help you out on that.
Hello.
Yeah, hello.
Yeah. So thank you, Puneet sir. Thank you for your presentation for today. So there is one announcement for the participants. The attendance will be updated by evening. Okay. And the drive link is already shared where the PPTs are already updated. So you can go in the drive link and find out the materials from there. So with this, we come to an end of day 4 of the program. So tomorrow is off. So next we will join on 5th of April, that is Monday, sharply by 9:30 a.m. So all the participants are requested to please join on 5th April by 9:30 so that we can start the session on time.
Okay. Thank you everyone. Bye bye. Happy long weekend.
Okay, bye sir, bye. Yeah, Devyanshu sir, Aditya sir's PPT is already uploaded in day 2. So day 3 of drive of the folder. Yeah, Puneet sir's slides will also be uploaded soon. However, Aditya sir's slides are already uploaded. Yesterday's slide was uploaded. And sir, how can we say, what can we ask in the quiz? So it will be, the quiz will be on Monday. So next we will join on Monday on the day when the quiz will be held actually. So during the quiz you will get to know. The questions in the quiz will be based on the topics which have been covered till now. It will be based on the presentation slides only. Yeah, it will be an MCQ. You need MCQ. There will be options given to you. You need to select one option. And regarding the attendance sheet, it will be updated by evening. So we request all the participants to go regularly visit the drive and the announcement pages. So once the things are done, it will be announced in the important announcement page. So you will get regular updates over there. Thank you. So we request all the participants to please get disconnected. We will be ending the event by another 10 minutes. Yeah, Asif sir, no, the MCQ marks won't be included in the certificate. Okay, thank you all. Thank you. Bye.